It's three slides that we are using here. Is that okay? It's going to be for the part one, part two, and part three. So when I finish, I'll sign everything. Is that okay?
Okay, sir.
Mm-hmm. And we did for this. Is that okay? Then I think, as of last week, did we do something we call the voltage regulation, where we spoke about Zener shunt regulator? I think we did this, right?
Yes, we did a winner. Yes, winner chance regulator. We did that.
And I asked you about this, and I said this is a summary of everything that we've been talking about in power supply. And
Yes.
I think we solved this question. And did we do something called a waveform?
Away from yes, we did this one.
Okay. So maybe let me start the recap from waveform. Okay. So as I last week, I was explaining that anytime we have a quantity, and the quantity is with respect to time, that it varies with time, we call it a waveform. Is that okay? So supposing you are getting money from the government, with time, every month the government has to send you some particular money because you're on the payroll, or you are in an institution, you are teaching for an institution. They have to be sending you money for every month. That is what we are trying to call it away from. Is that okay? But this quantity that we are talking about, the yours is a month. We are talking about seconds here. Is that okay? Some goes down to milliseconds and nanoseconds. So anytime there's a variation of this quantity and this variation goes with the varying of the time, we call it a waveform. And this quantity can be a whole lot of them. We can have, say, voltage. And when we even look at the first diagram that we do have in here, the first one here, you see there's time here and there's voltage here, you see. So the quantity value here is voltage and is varying what? With time. And that is what we call a waveform. So anytime you see a plot like this, you can call it a waveform. And it's not always going to be kind of a curve like this. It can be a rectangular one, it can be a square one, it can be a triangular one, it can be in so many forms. But what you have to put in mind is the quantity varies with what? With time. And then look at even the second one, it's not voltage this time around, it's current. The quantity can be voltage, it can be current, it can be EM field, it can be magnetic flux. Every quantity you see that varies with time, we see what is a waveform. But most importantly, this waveform can be in one direction or it can be in two directions. Is that okay? In their variation with time. When you say one direction, it means it's taking only the positive side. When you say a two direction, it means it takes the positive and takes the negative simultaneously. Is that okay? And when it's taking only the top one, or say the positive only or the negative only, we call it as a unidirectional waveform. That is only one direction waveform. So when you look at something like the A is only one direction. When you look at something like the B2 is only one direction. When you look at something like the C, is between the positive and the negative, because the waveform doesn't reach only the positive. It goes at the positive and extends down to the negative. Is that okay? With time. So here we say it's two directions, and that is what we call the alternating waveform. Is that okay? So if we have a positive and a negative extended on that waveform, we call it an alternating waveform. If it's only the one direction, we call it a unidirection waveform. And the one direction here can be, what I've shown here is only positive, but it can be only positive, it can be likewise what? Only negative. Is that okay? So please let's note that. And a very typical example of unidirectional waveform is what? From what we've learned so far.
That's DC.
DC.
Perfect. It's a DC. And a very typical example of an alternating waveform is what?
AC.
AC.
AC. Perfect. It means you understand what we are doing. Very good. I'm proud of myself and everyone here. Okay. So A very typical example too again is something that we call a sine wave. And if we have, let me try something here and let you see. So a minute here. So I'll stop sharing this one and I'll share the entire screen. Share entire screen. And if you can see my entire screen, then you let me know. Can you see my entire screen?
Yes, sir. We can see.
Okay, right now, what do you see?
I can see even mature records.
Okay, let me
MATLAB, yeah, MATLAB. A
MATLAB, very
MATLAB
good.
something.
So I'm just using MATLAB here. I want to show you something here. Is that okay? So if you have something like, let's say some X values, and the X values here, let's make this one big. Mhm. The clear bars here, don't worry about it. But we have some X values here, and the X values, let's say we do a mean space of 0 to say 1, or let's say 100 or 10 maybe, and a difference of 0.1. And we call another function as y. But this time around, we let y be a sign of this x. Is that okay? When you run this, we're supposed to get some values for the x and some values for the y. Now, if we do a plot figure of coming, or maybe let me just do 1 to 100. And let's do some figure. See, we do a plot of, say, the x against y. Let's see what we will get here. Okay, this is too much. So we have this one and this. Maybe let me make it 10. Okay. So can you see something here?
Yes, sir.
Very good. So this is not very smooth because of the number of variables that we've used. Is that okay? But if I use a division that is very small, you will see a very nice waveform because of the sign function that I'm using here. Is that okay? So that is just by the way. So what I'm trying to say is, let me share another thing. What I'm trying to say is if we have a sinusoidal wave, it looks almost like what we have here, depending on the variables that you use. If the intervals is very small, you get a very smooth one. If the interval is that it varies that much, you get a very rough one, like what I just did. Now, if you have something like this, it's almost representing or looks like how an alternate waveform looks like. And this coming weekend, again, is going to be a practical session. And here I will show you when we look at an AC, how it looks like. An AC ideally looks like what we have here. Is that okay? It behaves the same as how a sine wave behave. When you connect it to an oscilloscope and you view it from the screen, you see that it gives you a very nice waveform like this. It means that the voltage that or the EFO that we are getting from ECG to our house, it gives to us with time. Is that okay? With some milliseconds. And that is what we can use the oscilloscope to observe. And that is how a sine wave to behave. So in a typical way, someone can call an AC as a sine or sinusoidal form. Is that okay? Because of how it behaves like a sine. Is that okay? Please, do you understand?
Uh, sir,
Yes, sir. Please, I'm listening.
yes, yeah. So yeah, this is very clear. And what I've been wondering is, yes, we are actually familiar with these sound waves,
Yeah.
but the other square waves and all that. What are some of the sources? Where can we get those waves from? And all that. If you can briefly say before we continue with this.
Yes. So this is a very nice question.
Good.
So the sine wave, the square wave, the triangular wave, and all other waveform depends on how we get our individual values. And when you saw what I showed, we can actually limit the values that we have in there, and we can get something like a triangular wave. Is that okay? Because of say the values that we are getting, it's not many as what we have here. When you look at
Okay.
a very nice one like this, it means within from this end we have a lot of variables in here, so it's easy to get uh, a, a nice curve like this. And it's the same as having some plotted values that you want to plot. Some of them you get a very nice one, some of them you not get a very nice one. Is that depending on the number of variables that you are given? But
Do
they
they
are
also define smooth waves? Are they smooth waves as like the sine waves?
come again.
So you are saying that it depends on the values of your plotting.
That is one thing, but I'll bring the next thing.
Okay.
But you ask your question.
Okay, all right. So I was asking whether they are also normal waveforms, like
Other
the
with
sine
yes,
wave.
yes,
Yeah.
that is the
Okay.
square that we are talking about.
Okay.
That the the values that I'm also talking about. But the very typical example of say getting another square wave is in communication, and it's in some other devices. Some devices they don't bring a square wave, sorry, a sinusoidal wave like this. And when we were looking at switches, I told you we have another form of a switch apart from the linear regulated one that we did. We have a switch mode. A switch mode may give you pulses, not a smooth one like this. Is that okay? So that one may give something like a square wave. Please do you understand?
All
So,
right,
but
sir.
a square wave and a triangular one, we mostly see it in digital means. Let's say in communication and say signal processing, or in other form of a switches. Is that okay?
Yes, sir.
And it's typically the same as we see. We have a sine wave like this, and after passing through the power supply, we get it straight line. Is that okay? If we have another sine wave like this, we can actually transform it through some semiconductors, and we can actually get a triangular wave or get a square wave, depending on how we want to use it. Please do you understand?
Yes, sir.
Okay. Please, any questions so far? Can I go on?
Okay, sir.
Mhm.
Yes, in physics, concerning the square wave, are they calculation related to them? Because if you look at the peaking of this wave, it's quite different from a triangular wave. We are going to experience some flatness at the top. Are there theory behind those type of waveform as well?
Concerning the square wave.
Yes.
Okay, so when we are talking about waves, we are talking about how the thing is giving us with time. Is that okay? So something
So,
like what we have in here. You see, it means the voltage is zero here. When it goes up here, we have some positive values. I'm using a
okay.
laser pointer here. It
Yes.
means we are getting some values with a particular time. Another
Uh-huh.
time comes, let's say, in another
So,
2 seconds.
at the top there, at the top they were experiencing flatness. That's my concern.
Okay,
There's something. Yes.
so
So
the
there.
flat is just a constant voltage or any quantity that is here that is being given. So if
Okay.
this is current, it means here it's giving you some current that is constant for a particular time. And the time is
Okay.
very short because this one can be milliseconds or nanoseconds. Is that okay? So
Okay.
we get it, then it goes down to off, then we get it up. Is that okay? And it's not
Okay.
like the sinusoidal that we have here. Is that okay?
All
And from
right.
your understanding right now, you know how the half comes in, and you know how the negative half comes in because of the alternate means. We have last week I showed you where we have one loop going this way, then we get a half, and another loop goes down, we get another half here. Is that okay? In the rectification procedures. Is that okay? So how the sine wave behaves, yes, it tells a lot about what is actually going on in the system. Is that okay? And we have all of these ones, but we will not go through all these ones. We are just interested in the sinusoidal waveform.
Okay. All right. Thank you.
Okay. So please, any question again before we move on? Okay, so I think we can go on now. So what I'm showing on the slides, I think you are very familiar with. You know what one complete cycle or series behaves, what it means exactly. When you say a cycle, you know that when you go halfway like this is a half cycle. When you go halfway like this is another half cycle. So when you add two half cycles, you have a complete cycle. Is that okay? So when I start from here and I end at the P, from the O here to the P here, I will say I've completed a cycle. Is that okay? The same way from the top here to this top here can be a cycle. And do we understand it that way, or I should explain that part? Because from here, maybe let me start from here to here. We know it's a cycle, right? From the is it 0 or O? So let's say O to P. Do you know it's a cycle? Do you understand it in that perspective?
Yes,
Yes,
sir.
please.
From the top here to this top here, do we know that it's a cycle?
Yes, please.
Very good. It's a cycle, and another thing that we can call this one is a wavelength. Is that okay? Because wavelength is from one crest, from an even wave definition. We say from one crest to another crest, or one trough to another trough. Is that okay? And one cycle two is a wavelength. So from the top here to the top here too, it's a full cycle because we have a quarter here, we have a quarter here. It adds up to become half, and another half here adds up. Is that okay? Then you get a full cycle. Now, if we want to know the time that it takes to complete that cycle, one cycle, we call it a period. Is that okay? And it's very important. So the period tells us, okay, if you have a period of 2 milliseconds, it means for every cycle, the quantity that we are giving to the time, we are giving with respect to time is actually what? 2 seconds within a cycle. And supposing we know that, 200 cycle comes in, we can also find the number of time. And we have something we call the frequency. The frequency is telling us the number of cycles we've completed within a second. Is that okay? So how many cycles do we complete within a particular time? And our house, we know the frequency that we get there. We know that, right? ECG is giving us 220 volts and at a frequency of what?
50 years.
50,
Very
50
good.
to 60 years.
Exactly. It means that what ECG is giving us, the number of cycles that they are giving us within every second is what? Is that 50 hertz? Exactly. So we have a frequency for it. Exactly. And that is the number of cycles within a second. So it means ECGs, the cycle they give us, all of them is what? Is in a second. And that is the frequency, because frequency is talking about the number of cycles. So we say 1 second, how many cycles have you achieved? Exactly. And that is what defines the frequency. And it's measured in what? In hertz, which you know. I've even written the answer here. It's 50 hertz because we are following the Great Britain electricity standard. Is that okay? So we are also using 50 to 60 hertz. So, but there's a relationship between frequency and period, which you know because it's inversely proportional. We have T to be equals to what? 1 over F. Uh, please, can we go on?
Yes, sir. Yes, sir. Let's go on.
Okay, so now, if we understand this, I want you to try this question for me. Please, are you there?
Yes, sir.
So please try this for me.
The product time for A, I got 0.02 seconds, and the product time for B, I got 0.05 seconds.
Have you, for the second one, have you converted the kilohertz to hertz?
Sorry, I didn't see that. I didn't see that.
So you have to convert it to kilohertz from kilohertz to hertz.
So in that case, do you have to divide by 1,000?
You multiply by 1,000.
Multiply by 1,000.
So then to be 2.0 times 10 to the power negative 4. 2.0 times 10 to the power negative 4. 4 seconds, sorry.
Yeah, hello.
Yes.
Sir Kujo, yes, I'm listening. Apart from Sir Kevin's answer, any different answer so far?
Yes. For
So
the second one, yeah, the second one, you will get either 0.005 seconds. In other words, if you convert that, you can get 50 microseconds.
yeah.
Any different answer?
For question
For
one,
the,
there's no question one.
Yeah, for question one, I think yes, 0.02 seconds and then 50 microseconds.
Yeah.
Okay.
Whereas the question two is 625 hertz.
Yeah.
625.
Yes.
Yes, please. Hertz.
Okay. Okay.
We
Yes.
converted the microseconds to seconds.
But anyways, what did you get for the period? When you have to find period, what did you get for the period?
For
For the
the
number two.
number two, 0.02 seconds.
If number two, is it B or the second question, which is an alternating current?
An alternating current completes 5 cycles. in 8 milliseconds. What is the frequency? But I just want to know the answer for them. Yes, could you answer for the period?
For the period, it has to be 1.6 meter-second. Sorry, millisecond.
Okay, that's good. Then from there we find the frequency, which we are going to get 600 and what?
25 Hz.
Okay. So the answers, they are all here. So we have the first one, the second one, and that of the question 2. Please, do we all understand? Because the way we are responding, I believe we all understand.
Yeah.
Say for the B part.
Okay, for
Hello?
the class, we have an alternating current that completes 5 seconds.
No, I'm talking about determining the period for the distance. I'm talking the B, 20 kilohertz.
Yes. So the 20 kilohertz, if you want to find for period, is the inverse of the hertz, but there's a prefix
Exactly.
attached. Is that okay? The prefix is attached, which is going to be 20 times 1,000. You get 20,000. Is that okay? Then find the inverse of it anyways.
Okay.
Okay, now let's go on to another important parameter that we have to know when you are dealing with electronics. And please let's know that everything that we are doing here, we've not even dived in very well with electronics, because we can actually do digital electronics, analog electronics, do the OR and end gauge and other stuff. It's very an interesting thing, is that okay? But supposing we get a chance, or anyone get a chance, then we have to do electronics too. I think it will be very interesting, because that is where we get to experience all these things very well. Anyways, we have something called the instantaneous values. And I use values here because it can be so many quantities. I told you that if we are plotting some quantity, that is the waveform. Is that okay? And now, Sarah, please mute yourself. That is the waveform. Is that okay? And now what we want to look at is the value, the instantaneous values. And here the values may represent all quantities I mentioned earlier. Sir, could you please, do you want to say something? Your hand is still up. Could you Anefi? Could you Anefi? Sorry.
Sorry, it was an old hand. Old hand.
That's fine. So here the instantaneous values, what I'm trying to say is the values here may represent any quantity that the question gives, or what you are looking for. It can be a voltage. And if it's a voltage, we are talking about instantaneous voltage. You remove the value and you put voltage there. And we are talking about EM field, it becomes instantaneous EM field. We are talking about current, it becomes instantaneous current. Is that okay? So don't confuse yourself with this. It can be in any forms at all. But most of the times, when we are dealing with electronics, or even in our lab, we mostly use voltage, because that is what we've been plotting against time a lot. Is that okay? But we can look for current too. We can look for EM field too. We can look for magnetic flux too. Is that okay? Now, the next thing that we also have to do is we have to look for something we call the largest value that hive cycle has reached. And that highest value is, we are talking about a value like this. You see the hive cycle here, the very highest peak here, and we call it the peak value or maximum value. And here again, the value may represent any quantity. So if you are dealing with voltage, it becomes what? The peak voltage. If you are dealing with current, it becomes the peak current. If you are dealing with EM field, it becomes the peak EM field. Is that okay? And it's very important. When we were dealing with waveform before in physics, I think I taught you waves. The maximum value was called what? Amplitude, as at then. Is that okay? But here, because we are dealing with a particular quantity with respect to time, it becomes what? The peak voltage or maximum voltage. If it's a voltage, and if it's EM field, it becomes peak EM field or maximum EM field. Now we can actually also look at the the peak to peak. When you say the peak to peak, we mean the maximum voltage you can get at 1/2 and the maximum one that we can get at 1/2. So if you measure that peak here to peak here, we call it what? A peak to peak. And again, I brought value in here because it can represent any quantity. So if it's one here, it's only the I started again. Hello. Now we can actually find the. Is my network breaking or it's fine? Because I can see some scratches going on here.
Yes, your network is
It's
breaking.
breaking, sir.
Sorry.
It's breaking.
So I think it's stable now. So we can actually find for something that we call the average value. Is that okay? And here, the average value here, in a normal way of math calculation, we are just talking about the area under the curve and the base of the of that particular curve. Is that okay? So we want to look at all the areas that is down here. And when you're talking about something like this, we can easily use, I don't know if you remember something we call the trapezium rules in calculating for area under a curve, where we will segment the curve into so many sections and we use the trapezium formula 1/2 times the height into brackets a plus b, and we do it for individual ones. Is that okay? So supposing we segment it into hundreds of them, we can find the integral of it. Is that okay? And integral is talking about the summation. So we can find the integral or the summation of all these ones. Is that okay? Then we can actually get the area under the curve. And of course, divided by the length of the base. And the length of the base is going to be just what we have here. Is that okay? Now, for this particular waveforms, we just have a very simple formula that we can use for a sine wave. And here it's just about multiplying the 0.632, which is also equal to the 2/pi by the maximum value. And I've told you the maximum value is the maximum value that we can get here. Is that okay? So if it's voltage, it becomes the maximum voltage. So maximum voltage or voltage, they are all the same. Is that okay? So if you multiply this one, the 0.6 by the maximum voltage or the peak voltage, you are going to get your average voltage, because we are dealing with voltage. If you are dealing with current, the maximum current multiplied by the 0.6 and you get what? Average current. Now, yes,
Sorry.
Bismarck.
Yes. I want to get this clear. The peak to peak voltage, the peak voltage itself, and then the average voltage. What is the significance of each of these voltage now?
Okay.
And which one eventually do we use?
Okay, so the one that we use, I'll come to that.
Okay.
You let me finish with the second slide, then maybe it will bring some explanations here. So we have something we call the effective value. And the effective value is just telling you the amount of power that the AC will give to you as compared to the DC. Is that okay? So supposing you have like your house, you have 220 volts. When we tell it to convert it to DC for us, comparatively, what are we getting? Is it the same or it's not the same? So that is what we are looking at. And ideally, if we have to do a straight conversion from our house, what we are getting, 220, we don't do a step down, we don't do anything. We can actually get the same 220 to a DC form. Is that okay? So in our house, what we are actually getting is called an effective value. And a typical name for the effective value, we call it the root mean squared value. And because it's voltage we are talking about, it becomes root mean squared voltage. Exactly. So ECG is actually giving us something we call the root mean square voltage. Is that okay? And that one is, I've even made a statement here, the British own. Ghana, we are following this British electricity procedure. The supplies that they give is 220 to 240. And it's the same that we are also getting. Is that okay? So in your house, what you are getting is not the maximum voltage or the peak voltage, or it's not the peak to peak voltage. It's actually the what? The root mean squared what? Voltage. Is that okay? And supposing we want to talk about it in respect to current, and you know the current that is actually coming, and you know the, of course, say the EFO that is actually coming, we can also relate all these ones to it one way or the other. That is why all of them have represented it with value. Is that okay? So the value is representing the quantity you are dealing with. If you are dealing with voltage, you move the value and put voltage in there. Is that okay? So when I give you a question and we are calculating for voltage, I don't want to see value. I want to see voltage. Or if it's a current you are giving in, you have to see current. So let's go back to what we are doing. The root mean squared. So ECG is actually giving us something we call the root mean squared. And if I want to actually find the maximum value or the maximum voltage or the peak voltage that ECG is giving me, there's a formula here that I can use. I just have to it's a 0.707 times the maximum what voltage. And I've told you ECG is giving us something about 220 volts. Is that okay? So if you want to find the maximum, we just have to divide the 220 by the 0.7 and we get a maximum voltage in here. Is that okay? So ECG is actually giving us more than what we think we are getting if we have to connect to an oscilloscope and observe. But what they are giving it to us, if you want to relate it in terms of the effective value, that is what we get it at, what the root mean squared voltage. Am I confusing everyone, or we are good?
Okay, so Sir Rabbi,
Yes, sir.
so from what you are saying, does that mean that though ECG is, let me assume 220, is giving us 220, but the actual value
that is the what they are giving us anyway.
They are giving us 220, but the actual value that we are getting is 155.
No, how did you get a 155?
I multiply it by 1 over root 2, like you have on the slide.
No, so what we are getting, ECG is giving us root mean squared. What we are getting from ECG is the root mean squared.
Is the root mean square rather? Okay.
Yes, it's not.
Then it means what they are actually giving us is 300 and something.
Very good. Around 311 point something volts.
Okay.
I think
Okay.
31. It was 313 or 312. The last time we calculated it.
Okay. Okay.
Is okay. Right. And that is what
Yes.
we are actually getting from ECG, and that is the root mean squared voltage. Is that okay? So from there we can actually find the maximum voltage if we connect to an oscilloscope. It can actually give us. Yes.
Why the surge in that value before getting to our homes? What happened?
Okay, so nothing happens. That is the actual value that it has to get to your home. Is that okay? That is why we are calling it the effective voltage. It's a ratio of the voltage that we want in terms of DC. So in actual sense, if even you connect a meter to read, you will read the root mean squared voltage. But if you connect to an oscilloscope to measure the actual alternates, you will see the 300 and something volts. Is that okay? If you have to read the peak voltage. Is that okay? So the values that is reaching us is not a physical value that we want to be seeing as 300 and something. It's supposed to be some value that we'll be seeing around 220. Is that okay? But the sinusoidal waveform of it may give us more than what we are seeing. And that is around the 300 and something. Is that okay?
Okay. Okay, sir.
Okay. Now let's look at something again. We can actually also relate look at how the waveform is actually coming. You saw I did one waveform and it was crooked. Is that okay? One waveform too will be very, very smooth. Now, and I told you there are a lot of factors that goes into that. One factor could be the average voltage, one factor could be the root mean squared voltage, one factor can be the maximum voltage and other things. But we have something that we used to measure for that. And that one we call it the form factors. We have another one we call the peak factor. Is that okay? And that one is just indicating how the shape of the waveform is going to look like. So when you have a form factor of a value and someone sees the value and the person is good with this, the person will know that, okay, the shape of the waveform will be crooked a little or maybe unbalanced a little, and That one is just informing us how the waveform shape looks like, exactly. Because how it looks like to influence how your voltage regulation tree is going to be, like how you are going to receive your voltage. So the form factors that you see here, that is what it actually explains. So you see a form factor here and you see a peak voltage, a peak factor here. It's just explaining how our wave shape is going to be like.
So you get this calculation where people can even predict how the waveform look like. Does it actually inform the safety of the waveform or the power supply?
Okay. So in real form, as in what we have in our houses, is a different thing
Yes.
altogether. But
Yes.
in real forms in power stations, in real forms in the labs, it's really considered. Is that okay? But our power supply doesn't just come straight to our house. It passes through a lot of stations, regulations, and other things before it comes to our end. Is that okay?
Okay. So we are expecting, if all things being equal, we are expecting acceptable form factor or peak factor.
Yes, that is supposed to be that. Yeah.
Thank
But in terms we want to do a build up of say a power supply or any other thing, we will have to consider these things in building it. Is that okay? Because you have to consider the maximum voltage, you have to consider the root mean squared voltage and other things. Is that okay?
Okay.
Now I have another question for us here, and I think this will be my last question. And then I'll end the slides and go to the part 3. Can you try this for me, Abed? Maybe I'll just give you 10 minutes for you to try. So the question is, the following table gives us the corresponding values of voltage and time for a half cycle of alternating current. So this is the chart, and this is just a half cycle. So when the time was 0, the voltage was 0. When the time was 0.2, sorry, the time here is not seconds, it's milliseconds. Is that okay? When it was 0.5, we were having 7 volts. When it was 1, we were having 14 volts. When it was 1.5, 23 volts. Up to the end here, we get a half cycle. Now, the question is telling us that, let's assume that the half cycle is the same as the negative high cycle. They are identical. So what you get at the positive is still the same as what you have at the negative. From this, what will be our frequency of the power supply? What will be our instantaneous voltage? Here we are dealing with voltage, so no values. Voltage of the voltage after 1.25 seconds, milliseconds, and 3.8 milliseconds. And we have to look for the peak or maximum voltage. Here we are dealing with voltage, not value. And we have to look for the average or the mean voltage, not value. And the last thing, we have to look for the root mean squared voltage, not value of the waveform. Please, do we understand the question? Can we try it out?
Yes, sir.
Please, let's try. So what I'm expecting from you is you have to do a very small chart like this. Let me see if I can draw something here. You have to do a very small chart like this. And you know that if we have a waveform, this part becomes our what? What quantity will be represented here?
Is the time.
Voltage.
No, look at down here.
No, it's time. That is time.
Very good. That is going to be time. Is that okay? And here I'm saying the time is not seconds. I did a mistake here. It's milliseconds. So ms.
Milliseconds.
And the ordinate here is going to represent what?
Voltage.
Voltage. Perfect. Is that okay? And you write your unit here. Ideally, we expect some to also go down, but let's just focus on the half cycle. From the half cycle, when you look at the range of values we have for the time, is from 0 to 5.
0 to 5.
Is that okay? So it means you are going to get 0 here, and you will translate, let's say, up to this end, say 5. Is that okay? So we are just doing a rough sketch of it in your book. Then when you look at the voltage, the voltage is from 0 to another 0. Is that okay? Meaning it goes and come back again. But the maximum voltage that we have here is what voltage?
maximum 76.
76, perfect. So we can do a 76 here to represent our maximum. Is that okay? And in our own book, we can do some small calibrations in here. Maybe here we'll start from 0.5, you go to 1, you go to say 2, you go to say 3, you go to say, do your small calibrations in your book without using a graph sheet. And do another small calibrations in here, represent your voltage. Maybe 10, 10, 10, 10, 10, 10, 10, to get to the 75. Now, the first thing that we have to do is to look for 0.5 and 7. So 0.5 is for the time. Let's say 0.5 is here, and my 7 will be around this end. So I'll just put my point here. That will be the first one. Then you locate the second one. Is that okay? So do that for me. If you're able to draw it very well, it will be easy for us to do the number 2. That is the B part. Please, are we done? Are we done drawing? Hello.
Hello.
Please, are we doing it?
Yes.
Great.
Against 14. Against 23. Point 5 against 56. Yes.
Hello, what's going on? Yeah, keeping.
Sir Robbie, we are on it.
Okay. So maybe if you are done, you can take a picture, then you put it on a platform, or maybe you can share it here. I think we can share documents here. Put it on a WhatsApp. I said WhatsApp. The message part. I will just look at it.
Okay.
I want to see what.
You want to see the graph, eh?
Yes, you can just take a picture. Then I think it's possible we
Okay.
can piece some. If we cannot, yes, sir.
They should put it on the WhatsApp platform so that we can also compare. Then we can also keep it as well.
No, I will not put my answer there. I want to see yours. Is that okay? So if you better still, let's not sign it. When you finish doing it, tell me, then I'll know how to go about it. So just draw a very simple one, a rough sketch. Then when you finish,
Sir Robbie, for the sketch, I think I'm done.
Great. So now let's go to the A.
Yeah.
So now the question is telling us to find for the frequency that is being supplied. And if you want to find the frequency, by now I should be expecting that you've done with, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, sir, Anefi. You should be having some plots like this, and you draw a very nice time cycle.
So the A, which is the frequency of the supply.
Yes. What did you get?
The frequency I got 100 hertz.
100 hertz. Okay.
Yes, yes.
Can you guide us through how you managed to get 100 hertz?
Okay, so what's the name? The thing is in half cycle.
Yes.
Half a cycle. So the frequency of the supply, that is a full cycle, will be twice the 2.5.0 milliseconds. So that gives us 10 seconds, and that is 0.01 seconds. And to find the frequency, it will be 1 over that period, which is the 0.01. So 1 over 0.01 is 100 hertz.
Perfect. Please, do you understand?
So please,
Yes.
come again.
Okay. Say, and if you can you help my madam for me? I beg.
Okay, so please, what I'm saying is that the values that are given there, they are for half a cycle. And to be able to determine the period for the full cycle, we need to multiply the half cycle by 2. So that means that the 5.0 milliseconds by 2, which will give us 10 milliseconds. And that 10 milliseconds will be equal to 0.01 seconds. So that is the period for the whole thing. Now we are looking for the frequency, and the frequency is 1 over the period. So if you got the period to be 10 milliseconds, which is also 0.01 seconds, then the frequency is going to be 1 on 0.01, which will give us 100 hertz.
Okay. Thank you.
All right, you're welcome.
Okay, so now let's go through. So basically what we are saying is, if we have a cycle, we are saying that if we are able to complete a cycle like this, that makes a period. Is that okay? The time that makes it a period. But in the question, we are giving only half of it. So and the half reaches here, and the half that reaches there is 5 milliseconds. Is that okay? So 5 ms. So it means if I want to find for the full one, I have to just multiply this one by 2. It means I need another half of it. Is that okay? And the question just stated it that the positive is the same as the what as is the negative. So if I want to reach this cycle, it means I have to get what 10 before I can reach here. And this is going to be my period. And it's in milliseconds. So if you want to convert it to seconds, of course you divide it by what? It's going to be raised to the power negative 3. So that is going to be 0.01 seconds. Exactly. Then of course you find the inverse of it to get your frequency. And that will be all. And I think you'll be getting hertz. Now let's go to the B part, if you all understand this. We want to find the instantaneous voltage of voltage after 1.25 seconds and 3.8 milliseconds. This is very simple. In your chart, try and trace for 1.5. Is that okay? So 1.25 is going to be, let's say if 1.25 is around this end. Trace it and let it meet the curve here. Is that okay? Then trace it towards the voltage part. And tell me what you get for this value.
Okay, so Sir Ravi, 1.25 milliseconds. I got 20 volts.
20 volts, okay.
And 3.8 milliseconds, 70 volts.
Okay.
So I have pasted,
and you have
I have posted
20.
my image at the page.
Okay, perfect.
The diagram, I've put it there.
Okay, perfect. Okay, this look good. Any different answer and anything on the page so that I can comment on, I beg.
Sir Abby, please, your explanation concerning the instantaneous that you drew on the graph, can you go over that one?
Okay, so after drawing the curve, what I'm saying is if you want to find its corresponding voltage, because we are giving time, so I want to know the voltage that I will get at a particular time. Is that okay? So look on the time. The time 1.25, where does it fall? If it falls around this end, draw a line to meet the curve at the top, then trace it towards the voltage part. Is that okay? So if you want to do like the 3.8 and say 3.8 is around this end of the time, is that okay? I'll just trace it to meet the curve I've drawn. If you do a very good curve, you should get a good range of value. Is that okay? And I think what Sir Matt said, he's around that range, so which is a little far. Then when you reach the curve, you trace it towards the voltage part. Is that okay? And that will give you the instantaneous voltage you are looking for.
Sarabi.
Yes, sir.
Yeah, I for the 1.3 I had 15 volts.
15, okay.
15 volts and 3.8 I had 68 volts.
Hello, sir. Please, is it 1.25 or 1.3?
1.25. And we have another one as 3.8.
Yeah, okay. I thought I heard him say 1.3.
Any different answer? Does it mean we are not doing it? I want an answer. Or what's going on? Give me an answer and let me give a comment if you are on path.
Sir, please, for 1.25, I had 16.
16, okay.
16 voltage, yes, sir.
Mm-hmm.
I'm doing the other one.
Okay. Yes, Sir Bernard.
3 points.
Sir, please, the 3.8, I had 70.
70, okay.
Yes, please.
Okay. So is that all? Sir Bernard, do you want to add up? Maybe add up for the last so that I move on. Sir Kojo Anefi, do you want to add up?
So please, I also had for the 1.25, 16.25, what is 16.25 volts.
Mm-hmm.
And then the other one, which is the 3.8.
You have to get 16. 16 is too small. Maybe 16. You said one. Okay, sorry, 16. I was thinking of 1.6. So 16, yes. Mm-hmm.
16, yeah. And then the other one, I had 71.2.
Okay, that's so. I think The first one within 16 to 20 is fine, but 70 is too much for the second one. I think maybe getting around 60 to 65 too is fine for the second one. Is that okay? So when you do a very good plot, you should be getting around that range for these values. Okay. So maybe let's move to the next question. The next question is telling us to find for the maximum or the peak voltage. What did you get for this?
Okay, so Sarah, before the peak voltage, I got 76 volts.
Okay, perfect. That one, even from the chart, you can easily see it. Is that okay? That is the peak voltage. What did you get for the mean voltage or average voltage?
Okay. So
The average I had 174.5.
174.5.
Yes.
Oh. Any 174 is too much, but any different answer? How did you calculate for yours, Madam Felicia?
Okay.
Sir, please, I added the voltage and divided it by 2.
Okay. Hello, sir.
All the values of the voltage and then divided it by
There's
2.
a formula for finding for mean voltage. Use that formula. Let me go back a little.
Okay,
so you see, if you want to find an average formula, an average or the mean voltage, this is the formula. We have average voltage or the mean voltage to be equal to 0.637 times maximum voltage. And from our chart, we know the maximum voltage already. Is that okay?
That's 76.
Very good.
Oh, okay.
So, any different answer for me?
So please, you said it's 0.0.
No, I've not mentioned the answer. I was
it's 0 point something times the.
okay. It's 0.637.
Okay.
So it's 48.412.
48, but okay. 48, around 48 is fine. Okay. So, in actual fact, you can be asked to indicate these things on a chart, on the same chart, because after indicating for this one and finding for the maximum, we can actually also show where the mean voltage is. And you know, if we have about 40 something, it means our mean voltage is appearing around this end. Then you write your value on top nicely, like 48 volts. Is that okay? Then that will be all. And this is going to represent our mean voltage. Now then, let's do the last one, the root mean squared voltage. Should I show you the formula for that one too?
Yes, sir.
So, sir,
Yes, sir.
it's 53.74.
53. Okay.
0.74.
Any different answer? 0.74.
53.732.
Okay.
Any different answer? Okay.
So it's 53.732.
Very good. So now we can indicate our 53 to around this one, this end, which is very important. Anytime you're given a question like this, after finding for each of them, you indicate it on the same sheet. Is that okay? You calculate it nicely, write it there, then indicate it on the peak. Is that okay? No, not peak, on the sheet. So where you have your halfway, you indicate it there. So supposing I've messed the one up, I saw it baby, so let me do another one. So if I have this waveform here, I can indicate the 48 that you said here, and I can indicate the 53 to here nicely. Is that okay? Then I'll write it beside it, the value, and I write this value to beside it. then that would be nice.
Sir,
Yes, sir.
Sir Rabi,
Yes, sir.
please, I beg you for the A part. My attention wasn't there. Could you please use a seconds to go over for me? The A part. I'm talking about the
Okay,
frequency of the supply.
so we have a waveform like this, and we are saying that half of this waveform was completed in only 5 milliseconds, and the 5 is here. Is that okay? And I told you
Okay.
this one is not seconds. It's supposed to be milliseconds rather. I did a mistake here. Is that okay?
Okay.
But if we are talking about period is completing a cycle before we can use the time. If this is 5, I can, in the same question, it said that the positive is the same as the negative. So it means I can draw a negative here. Is that okay? And if I have this place as 5, it means that this N2 will be my another 5, making 10. So from here, where I complete this, it's going to be.
I was not hearing anything you say. Is it from my end, the network?
I don't know. Please can.
So we can hear you. It seems it is end. We can hear you.
Yeah, I think it's from his end. It's from his end.
Yes, Ibrahim, do you know something? This is a pre-recorded video, right? So you just take your time, then go through the video. Then if you have a question and you still don't get it, then you bring me on board and I'll explain it. So you just don't worry. If it's only the A part, just go through the video part. Is that okay? And I think the network will end.
You were explaining it, so I was thinking. I mean, you proceed. I mean,
you are not hearing me. That's why I'm saying that.
I can hear you say.
Okay. So I'm saying that if you complete half a cycle, in the question we are giving it as 5 seconds, 5 milliseconds actually. So when we reach here, this is 5 milliseconds. In the question again, they said the positive is the same as the negative. It means if this is my 5 seconds, another 5 seconds has to add up. And for me to complete a full cycle, I'm going to get what? 10 milliseconds because of the 5 plus 5. Is that okay? Now I get my 10 milliseconds for the period. If I have period, it's easy for me to find frequency because period is inversely proportional to the what? To the frequency. So I get my 1 over the P here. That is my period. That will be equals to what? My frequency, the F. And that is all. Then we get for our answer. Is that okay? It's a millisecond, so you have to convert it to seconds before you do that. And you're supposed to get around, what did we get? Is it 100?
Yes, please.
Yeah, get 100. You get 100 hertz. Please, do you understand?
We get 100 seconds or 100 hertz. I'm talking about. You are talking about the frequency. Okay.
Yeah.
Okay.
The period we get 10 milliseconds. That is 0.01 seconds. If you are converting and removing the milli, then when you finish, you find the inverse of the.
Then 1 over the period. Okay. Okay.
And that will be all. So I'll give you the slide. So kindly go through this particular question too. This question we are giving the mean voltage and we are asked to find the maximum voltage and the root mean squared voltage. Is that okay? There's answer here though, but still go through a bit. Now, so this will be the end of our part 2. Let me share the slide for the part 3. The part 3 is not really plenty, so we'll finish right now. Should we have to go for a break and come back later, or we should just continue?
So since you said we finish right now, I suggest we continue and finish.
So I suggest we continue.
Okay, perfect. Now let's go on to this one. So if you can see the slide, then let me know.
Yes, we can see it now. We can see it now.
Okay, so what we are coming to do here is basically transistors. Is that okay? As of now, we know semiconductors, we know diodes, we know power supply, we know one important function the diode plays in a power supply as a rectifier and even in voltage regulation. And now we want to look at another thing that we call the transistors, which is very important. Now, when you're talking about transistors, we can have so many complex ways of it. Is that okay? And it will have a lot of applications. One typical example is you are in church, then you speak in a microphone, and everyone in one in that congregation can actually hear you speak. Is that okay? No matter how the auditorium is, you speak through a microphone and everyone hears you. It takes that your weak signal, that voice, that very low one, and it makes it very big. Exactly, it amplifies it, and transistors does a very wonderful work in there. Now, transistors transitioning has started a very long time. Anyways, it's not now that we have something called transistors. It has been there for a very long time. And first, it used to be in a vacuum like this. When I say in a vacuum, you remember this incandescent bulb. Do we still have some around? I don't know.
It's been a long time I saw one.
I think we still in my lab here we still have some though, but that one is not where I am. The top there. When you came for, have you done optics experiment?
Sir Rabbi,
Yes.
when we went for the experiment, you see, there were these small bulbs that you can use, like you can put it in a torch. Small bulbs like that. Are they also incandescent?
No, incandescent is titanium. They used to call it they call it
Jolly
jolly
bulb.
Very good.
I know. I'm only asking that small bulbs that we use at the lab.
There's a small box.
Bulb, small bulb. When we yes, when we come to the lab, that small bulbs,
yes, I think that one too can be in it because it's in a glass. And okay, anytime you have something like a glass like one, and it has some filaments inside there, we can classify it in the form of a vacuum. Is that okay? Because there's a little less air pressure there, and it's only the charges that we have there from the anode and the cathode that creates the light for us to see. Is that okay? So the anode is there, the cathode is there, and that's more charges that is being transferred there. A site, and we get that light. Exactly. So if it's using that phenomena, it falls under this vacuum I'm talking about. So first, this is how transistors were. Even diodes were in a vacuum, and you can imagine it as very, very big. Is that okay? I'll show you a picture of one. And then, with time, we've transitioned a lot. As at the 1948, I'm sure by that time Ghana was still doing slave trade, but we were not having independence. Our independence came at 57 or something, right? We were not even having independence, but the whites were creating something called the transistors. Very marvelous thing. And they were transitioning from the vacuum state, something we call the solid state. It's okay. So now we had all the same conductors we are using is a it's a solid state completely. It's okay. We call it a solid state semiconductor. A solid state semiconductor basically is telling us that we are removing all the mechanical part and the vacuum part. Is okay. And even your laptops. First, you buy a laptop and there's a fan inside, and we have a hard disk we call the HDD. Is that okay? And that one it boots. And if the HDD is even running, you see that some fan moving inside. You hear some crank sound. Sometimes if you on your laptop, it will make some noise crank before it boots. Now we are transitioning from all these laptops or all these kind of a thing to something called the solid state. Is that okay? And the solid state is just a compact thing, and it's very, very, very simple in that way. And we can actually make it very small one way or the other. That you don't need any mechanical movement inside before you can retrieve information. Is that okay? And it makes it very fast and convenient to use. And semiconductors has been really, really transited from that end. So first, it was something like this. Then through a lab called we call the Bell Lab, and that is where Nokia came from and other things. It's a big lab on its own. So they are in charge of how the revolution of some of these semiconductors we are using, how they came into existence. And even as of now, we have a semiconductor as small as this, a transistors that are super integrated together. We have a lot of them that is, we've made it very, very small, and we call it some of them microchips. And not the microchips you use in your phone, but the microchip as a microprocessor. Is that okay? And it's a lot of these semiconductors that, or transistors that they fuse to become one. Is that okay? And maybe you've heard of something we call the IC, integrated circuit. And that is what we've transitioned to now. So your phone you are using, or any gadget you are using, next year the same company will come that they've modified the phone, they've added more specifications to it, they've increased the RAM, or they've increased the chip inside, and they will sell it to you, because that is how we are transitioning it. So as more as this, they'll add another features to it, add another transistors and other things to it to make it very more efficient, and they'll sell it, because the phone that we used to use, or the laptop we used to use in 19s or 2000s, early 2000s, how it used to boot is not the same as what we are using. And you saw how I did the plot for you to see. Just a click and I just get a plot. Just a click and I just get a plot. It's not going to take time for it to run. My laptop is very small, but I'm using it to run MATLAB, Python, any programming language. Is that okay? That is how we've transitioned to now. Is that okay? So as small as the chip, very efficient, works perfectly well. Is that okay? Another year, I'm using a MacBook. Another year, they will come again that we've increased the ability of the chip, and it all depends on the IC thing. Is that okay? They increase its ability, add more ICs and more transistors and other things to it, make the chip very, very, very powerful, and they'll sell it to us. And of course, we will buy because we want powerful things and efficient things. Is that okay? And they'll be transitting it to us every year and every day. So this thing is really very important, one way or the other. Am I confusing you, or we are good?
We are good to go, sir.
We are good.
Great. So there are a lot of applications in here. We can talk about transistors as amplifiers. As I told you earlier, you speak in a microphone, everyone hears you. You speak on even on phone, we have some amplifiers in there. You put it on loudspeaker, everyone in the room can hear, and all these things. Another important application of a transistor. Hello.
Hello, sir.
Yeah.
Hello.
Do you remember?
Sir Rabbi, your line went off a bit.
No, I'm saying that the semiconductors, that the rectification that we did, which of the semiconductors did you use? We don't remember. Hello.
No, sir.
We did rectification and the power supply. And which of the semiconductors did we say it converts AC to DC for us?
Use that would say.
The
Come
NPN.
again. Yeah, no.
Use that would say.
We use diode. It's okay. We use a diode to do that. And even with that one too, okay, I'll bring another question later. So a transistor can also serve as a rectifier. Is that okay? But we use diode in that power supply. Transistors too can also serve as a switch. Is that okay? First, we used to use these relays and other things, but we are using of late we are using transistors to do that. Please, can I go on?
Yes, sir.
Okay. Now we have something that we have to look at. I told you that transistor can serve as an amplifier. An amplifier, of course, increasing the signal for us. So you have a weak signal and it will make it very big for us. And we can actually measure how much this signal is being increased. Is that okay? So I'm talking, and you can hear it very loud there. We can compare the loudness that we can hear and compare my voice, and we measure how loud it has been increased. And that one, we call it gain. Is that okay? And it's an important thing here. So gain here measures how much the signal has been increased. Is that okay? Now, let's look at something again. When you're talking about amplification, there are two most important things that we need. The amplifier the churches use, the first thing that it needs is a power source. Is that okay? You have to give it a DC power source. It needs energy so that it can do the conversion for you. The next thing that it needs is a weak signal you are giving it to it. If the amplifier is there, there's no way to amplify anything if signal is not being fed to. Is that okay? So it has to get a signal before it can amplify it for you. And of course, when you are talking about this input signal, we can have something like a voltage, we can have something like a current, we can have something like a power. Is that okay? It can do all this conversion for us. So a typical example is what I've drawn here. This is my amplifier, but I told you it needs a DC power source. So you have to connect a DC power source to it. The first thing that it also needs is an input signal. And you see how weak this signal is. The intensity is very low, but after being passed through the amplifier, it goes up. Is that okay? And as at this time, when you say these waveforms, you have to understand them because I've explained them. Is that okay? We just did waveforms. Now, if we are talking about the gain, we can have voltage gain, as I mentioned earlier. We can have current gain. We can have something we call the power gain. And the gain is just the output of what we've gotten divided by the input that we give. Is that okay? So the output signal divided by the input signal. The very loud one divided by the very weak one. Is that okay? So if you're talking about voltage particularly, it means that the V out, the out that we had divided by the in, is that okay, can give us a voltage in. And of course, the current is going to be the I out over the I in. And of course, if you want to find the power, we can just multiply these two. We can get, because power is equal to what? Current times voltage. And that will be all. Now, I want to ask the class a question. What will be the unit for the voltage gain?
So, Rabbi, I think there will be no unit.
There will be no unit. Okay. What about the current gain?
That's a no unit.
The same thing, no unit.
What about the power gain?
What?
Okay. What are you sure about the what?
Yes, please. Okay, what?
I think it will have no unit as well.
Let me see.
Okay. So that one too, you will not get any unit for that. Is that okay?
Unit. Yes.
So now let's look at something here. Some of the applications of it, and we can have something we call the voltage amplifiers. We can have something we call the current amplifiers. We can have something we call the power amplifiers. But there's an important thing that I want to actually raise here. If we have a transformer and the transformer is a step-up transformer, is that an amplifier?
Hello,
Yes,
sir.
sir.
Yes.
I think it can be considered.
Amplifier.
Okay.
Because it steps up or it increases the voltage from a known source to the one we need. So I can classify step up transformer to be an.
Come again.
Yes, sir. I'm saying that I would suggest that step up transformer acts as an amplifier because there is a boost or there is a change in the strength of the volt from one form to another, an AC volt.
Well, sir, I think it cannot be considered as an amplifier.
Can you justify it?
My reason is that yes, even though they are both raising voltages, but they work differently. What's the name? The transformer doesn't need an external source of power. Sorry. Sorry. The transformer doesn't need an external source of power. Unlike you already stated concerning the transistor, that two important have to be available, which is the external source of power and then the signal.
Mm-hmm.
Yes,
Okay.
but then the transformer doesn't need any external source of power.
This do you know I've actually
Hello,
not thought
sir.
of. Yes, sir. So I'm coming in. I'm about to say,
Okay.
and if you
I also want to give my opinion.
yes, a minute. So Anif, we are actually bringing a very nice point, but I will not lie to you. I've never thought of it in that perspective. My thought is always in the mathematical ways, which I've been using it to prove for that. But bringing this one is very innovative. Like I understand your point, and it also makes sense. Is that okay? So thanks for that. Yes, Sir George, can you come on board?
Sir, but the transformer needs it also needs external source of power. The only difference is that the transformer needs, because the transformer will only step it down or step it up, but it doesn't also produce its own power. It is not a source of power. It only step it down or step it up. So the part that my brother mentioned, that it doesn't need a source of power, all the two require source of power.
So what he's trying to say is, you see, when we're talking about amplification, we said that the amplifier needs two things. It needs a DC power source and an input signal. A transformer can work on an input signal and make it
Okay,
a
then
high
this
power.
one, then that
But it
this
needs a
one
DC power.
doesn't have the input signal.
The transformer, very good.
Yes, sir, but this one need AC, right?
Yes.
Yeah, and then so I think the main difference is the input is the signal, is the input signal. But all of them require power to operate.
Yes, all of them requires power. So, but you see, the transformer needs an external source. Sorry, amplifier needs an external source of power before it can operate. But the transformer doesn't need it. Is that okay? Transformer, you don't need to give it an external source. You just give it the input or the primary, then it gives you a secondary one. Is that okay? And that is all.
But if you say external, it means you don't produce it. So the transformer too doesn't produce it, or does it produce it?
You see, what's the name? The voltage is staying the same with the transformer because it's only converting primary to secondary. You understand, George? So the power stays the same.
I don't understand what it is doing the transformer.
What do you mean by the same? Because it steps it up, so there is no way they will be the same. The volt
They will not be the same.
So
the power.
well,
I'm talking about the power, not the voltage. The power stays the same, not the voltage.
How?
But then you are increasing voltage from primary to secondary coil, of course, using electromagnetic induction. And then what you are saying here is that, or my point is that, the transformer is basically a passive device. It doesn't necessarily.
It's not a passive device. It's not a passive. It's an active device.
It's an active device. It's not a passive. It's an active.
Now, if it is a passive device, then it will only be a passive, like a conductor. And even conductors cannot be regarded as passive device because if the conductor is not a good conducting material, it may reduce the conductivity.
Hello.
Anavi, your argument is that for an amplifier, we need two things. That is an external source of power and also the input signal.
Yes, please.
And here for the transformer, what George is saying is that for the transformer, the input device is the voltage that is coming in.
Okay.
George, are you with me? George.
We are listening.
Yes, I'm with you.
Yes. So you are
I'm
saying
with you.
that, yes, you are saying that the input that is coming in is the voltage. So here, what is the signal that we are going to give it to the transformer?
That is why I'm saying that. Then the cardinal difference will be the signal. But for the input, all of them require external source because they don't produce their own energy. So I'm saying that the difference is the signal and not because we have transformers that also operate on current. So we have the current transformer, we have the voltage transformer. So even if the transistor operates on current, all of them can also make use of current. So the cardinal difference will be the signal.
Input signal. Okay.
Yes.
So Rabbi, I think you can take it from there. So here the difference between the amplifier and the transformer is that one, for the amplifier there is an input signal, but for the transformer there's no input signal.
They all have some
that is my argument. That is my argument.
But anyways,
if they all have it, fine then.
Let me bring in the explanation towards this one. What I was saying is what CNF was bringing was innovative in a point of comparing the things that we need for this one and the things that we don't need for the other one. Is that okay? But mathematically, we can actually use this one to prove whether a transformer can be classified as an amplifier or can be classified as not an amplifier. Is that okay? So before we do that, let's try and do these two questions. Then you see, even I've added it in the question that the last question is a transformer and amplifier. But before we do that, let's try and calculate for the number 1 and number 2. Without even calculating, maybe when you look at it, I'm sure you can see that. You can tell me the answer. So the first one is calculate the power gain of an amplifier that has a voltage gain of 5 and a current gain of 100. What will be the power gain?
500 watts.
500 watts. So by this time we will not get any units because it's a voltage gain and a current gain. Is that okay? They all
Yeah, so the unit cancel out.
We don't even have unit to start with.
Yes, so there's no unit at all. So 500 there is no unit, 100 there is no unit. So just 500. Is that okay? That's the power gain. Then the number 2 is if the transformer steps up a voltage of 10, then it steps down a current dash times. What will be the answer of this one?
Okay, so
let's look at this thing very, very well. Here we are not talking about amplifications, we are talking about transformers. So if a transformer steps up a voltage of 10 times, then it steps up the current dash times.
The voltage step up. The voltage 10 times. Then the step up will be.
Sir. Hello.
Yes, I'm here, please.
I think that it will be the reverse because the formula is V is equal to IR. So when this one increases, this one will reduce, right? So it means that this one, you can do it this way to be 1 over 10.
No, use the formula. I've given you a formula that we can use to do a kind of a question like this. We have a formula like P of that's the power of the primary to be equal to the P of the secondary.
Okay, then I remember the formula, but I am working, so I can't do that. That's why I'm doing the explanation. So when I get there, I guess.
And I saw that for the P is equal to I, so we're going to get IP multiplying the VP. Is okay.
No.
Then at the end, we expect that we're supposed to get IS multiplying the VS. Is that okay? If you are making these things a subject, it means that at the end of the day, we are going to get VS over VP. And we get IP over IS. Do we remember a formula like this?
Yes.
Primary current over
And the transformers, we did
secondary
this.
current.
Yes.
Yes.
Secondary
The primary
voltage over.
force and the secondary force.
So if you remember this, what would be the current? Because here the question is asking that if the transformer steps up the voltage of 10 times, then the current step down, then then it steps down the current how many times?
It will be. I think it will be the same distance. Or
Let's look at it very well.
Thank you. Hello, sir, Rabbi.
Yes, sir.
I think I got 11 times.
11 times. Oh, interesting. Will I be correct if I say the formula that we have here is equals to 10?
Yes.
but sir Rabbi,
Yes, sir.
per your distance, where we know that what do you call our input power is equal to output power. Let's say our VI is equal to our VR. So let's assume that we are talking about the transformer. Let's say V secondary is equal to, let's say, what do you call, V equal to, if the transformer step up the voltage 10 times, then the step down the current. So I was thinking, if you're having our VI is equal to, VI for primary is equal to VI for, let's say, secondary, and looking at the distance, the question, then we can simply say
when you have a transformer like this, and this is your input, we have our coils here. Is that okay? And we have our output here. And of course, our output too has its own coils here. Is that okay? This kind of a transformer, what is going in is the primary, what is coming out is the secondary. Is that okay? We can actually find for the step up or step down here. And you know that already. And we say that if you are finding for a step up and a step down, we are considering a formula like this. Is that okay? And a typical step up, we expect to get a value more than 1. A typical step down, we expect to get a value less than 1. Is that okay? From our formula that we have here, Vs over Vp is typically what the question is telling us. The question is telling us that the step up of the voltage is 10 times. Is that okay? It means our Vs over Vp is 10. Do we understand it to this end before I go on?
Yes.
Yes.
Very good. So now our step up is 10. But now the question is also interested in our step down current. Is that okay? If you want to know the step down current, we have to do a division of, and you know, if we are calculating for what we just did, the amplification, we are looking for the gain. It's always the output over what? The input. Very good. So now this one is over my input. Is that okay? And that is what the amplification taught us. But in our formula that we've gotten here, the Vs and the Vp is not for current. It's not IS over IP. It's IP over IS. So if I want to relate it to the amplification, I'm going to get 1 over 10 here. This is my input down here. Am I confusing you or we understand? In terms of amplification,
continue.
Yes, in terms of amplification, is the current output over current input. In terms of transformers, if we are calculating, is IP over IS. Is that okay? And we can relate that one to voltage, which is Vs over Vp. And the question gave us as 10. Is that okay? So if we want to actually find for that of the I in terms of the output here is going to be the what? The secondary. Here is going to be my what? My primary in terms of transformers. And here it's not like that. It's the inverse. Is that okay? So if I want to find the inverse, it means I have to find the inverse of the 10. That is why I have 1 over 10 here. So ideally, if I want to find the step down of the current, is going to be 0.1. That will be my step down of the current. And this one makes sense because anytime we are using a voltage transformer, we step up a voltage. The current doesn't behave that way. It goes down. Is that okay? Because of the formula that we have here. IP over IS is equal to Vs over Vp. Now let's look at something here. The answer that I've gotten here is my current gain. Is that okay? The answer that I've gotten here for the vein is my voltage gain. Yes, I think we have some hands up. Yes. Sir George.
Oh, sorry, sorry, so I'm working. Sorry. Where I am, I can't talk now.
Okay. So now let's look at something. I have my current gain, I have my voltage gain. I want to calculate for the power gain. Now, if my power gain, do you remember the formula for the power gain? P equals what?
IV.
Is equal to power voltage gain times current gain.
Times current gain. Very good. Now here, from the question and from the answers we've gotten here, my voltage gain is 10, and my power gain is what? 1 over 10, or 0.1. Is that okay? What would be the answer for my power gain here, please?
That should be 100.
It should be 1.
It will be 1. And okay, if we have a power gain of 1, does it mean the amplification is changing the weak signal?
No.
It's not doing anything to it at all. So the signal you give to it is the same output that is going to give to you. You can't do anything about it mathematically. Is that okay? So ideally, there is no way a transformer can be classified as an amplifier. Is that okay? So it has two different relations. If transformer is working on a voltage, it's working on a voltage. If it's working on a current, it's working on a current. That is all. Is that okay? So transformer cannot be classified as an amplifier.
Yes. So basically, it does not necessarily increase the power.
Yes, it doesn't necessarily. Yes, very good. The transformer doesn't necessarily increase the power. What the transformer is doing is targeting only the voltage or current, targeting only the current. Is that okay?
So Rabbi, if I understand you well, then it means that if the transformer targets the voltage, and let's say it steps up the voltage, it will automatically step down the current.
Relatively, yes. From our formula.
Okay.
It can't work on both at the same time. It works on only one. Is that okay?
Okay.
So now let's go to the actual thing that we have to do, that is the transformers. Sorry, the transistors. So transistors, they also provide voltage gain and current gain. And you see that I've written even it here. Is that okay? So transistors are good at this things. And if it's able to give us two of them alternatively, that makes it what? An amplifier. We have two types of it. We have the bipolar and we have the field effect. Is that okay? And it has a long family. Under the bipolar junction transistors and the field effect, under this we have the NPN, which I'm sure you've heard of it before. We have the PNP. Under the field effect, we have numerous of them, a whole lot. Is that okay? To the channels, we have numerous of them. We will not be using this tree. The only tree we'll be going through is this end. Is that okay? So we'll be talking about what we call the bipolar junction transistors. We'll be talking about the NPN transistors. We'll be talking about the PNP transistors, and we will end. Now, under the bipolar, we have two types basically. We have what we call the NPN, as I said earlier, and the PNP. And it has three different configurations, or let me say chambers or terminals. We have something called the emitter, we have something called the collector, and we have something called the base. The structure of it that we mostly draw is something like this. Is that okay? And the schematically symbol that we mostly draw is something like this. And the building block of it that we mostly have is something like what we have here. Is that okay? So I've made 3 columns to represent these things. We have the structure, we have the schematic symbol, and have the actual structure of it. And you know, as we know from semiconductors, you know that semiconductors, we can use a silicon to make that material. We can use a germanium to make that material. So you can have a diode that is made of silicon. And now you know that. And you can have a germanium that is made of silicon. We can have silicon that, a diode that is made of germanium, unfortunately, sorry. We can have a transistor too that is made of either silicon or germanium. Is that okay? So we can have a transistor. They will tell you that this transistor is made of germanium. This transistor is made of what? A silicon. Which, of course, it has been doped. And we look at it very soon. There's one important thing here. You see, most of the transistors, I'm sure you've seen it one way or the other somewhere. You see, it's either the back is cased or all the surroundings too is cased. And this is because of heat. Is that okay? So the heat is just connected to help dissipate this heat out. Let me show you a picture. So these are all transistors. You see there's a metal here that is actually back here. And there's a metal here too that is cased around in here. Is that okay? And I told you earlier that we have 3 main sections when it comes to the transistor. We have the emitter, we have the collector, and we have the base. And of course, we call it a bipolar because of the carriers that it have and the movement that is going on. And there's an important thing here that we have to know before we move on. And please try and understand this because the subsequent slide is going to be built on this. When we have a typical NPN, always we have the emitter down there, we have the base at the middle, and we have the collector at the front there. Is that okay? Let me show you the schematic. It's the same thing. The collector, the base, and the emitter. The only two difference that we are getting here, can we identify it? Between the NPN and the PNP. Can we see the difference between them?
Yes, sir.
Please, the arrow for the NPN, the arrow is going to the emitter. For the PNP, the arrow is going to the base.
The base, perfect. Is that okay? So this way I can use it to differentiate it easily. Is that okay? Anytime you see the arrow pointing to the base, it means that place is the emitter. And everywhere that you see a transistor, this line represents the base, and where the arrow is going will show us whether it's the collector or the base. Very good. Now,
Sir, please. Sir, hello, sir.
Yes, I'm here. Sir, this now.
Please, why the convention? Is there any reason behind the convention?
Which convention, please?
The arrowheads. One is going into the base and then one moving out of the base.
Not necessarily. When we are talking about the two of them, internally it's just between the holes and the electrons. Is that okay? But when we are talking about, we talk about something called the common emitter, common base, and common collector. That when we
Yeah.
reach the convention will make sense there one way or the other. Is that okay?
Okay.
But for the schematically like this, we don't have anything. So now let's go on. Now I've made a very small chart here, which is very important. For the emitter, the base, the collector, they are all three different sections that are together. When I say different sections, the emitter is heavily doped. Is that okay? And anytime you see an n-type, the excess is going to be what?
Electrons.
Perfect. The excess is going to be electrons.
Electrons.
It means this is not a normal doping. We have, when you say heavily doped, it means we've super doped it to have a lot of electrons in there. Is that okay? And anytime you see a p-type, the SS is a what? It's a hole. Here is doped, but it is slightly doped. Is that okay? And we have another n-type here, but it doesn't behave like the emitter. That one is a collector, and it's very, very, very lightly doped. Is that okay? Like very, very lightly doped. Now, let's go on to, maybe let me do a little recap here. If you remember our diodes, when we are having, say, two junctions and two types that we've merged them, and supposing this is my P, and supposing this is my N, and I have a potential difference in here, and I connect it together like this. This is my polarity, and this is my positive, and this is my negative. Then I connect it to the N type. What type of bias is this?
Forward bias.
Forward bias.
Very good. Now, when I do a connection like this, and I replace it with what I have inside, what will be the bias here?
Reverse.
Reverse bias.
Very good. Now, let's talk about the forward bias. If we are talking about forward bias, what mechanism goes in there? What is happening in between the two types that I have here? What is in between here?
P junction.
It is a junction. That is a depletion layer. Is that okay? Perfect. Now, if we have a forward bias, what happens to that junction here?
It narrows.
For the what? For the forward, right? What about the reverse?
It enlarges or it widens.
It widens. Very good. Now, let's look at something here again. Now, I have three junctions. I have one here, and so I will divide this one into three. So the first one is my N. The second one is my P. Sorry about my writing. And the very last one is my N. We are talking about this kind of a transistor, TNP. Is that okay? Now, let's forget about the last one that I have here. Or better still, let's forget about this last one. Now, let's connect a potential difference to it. And this is my negative, and this is my positive. And I connect this one to this last one in here. Do we see a bias here? Forget about the last one here. It's there, but still forget about it. Do we see a bias there?
Yes.
It's forward bias.
Yes, there is.
Which kind of a bias will be this?
Forward.
Forward bias.
Perfect. Because we have a positive here going to the positive here. We have a negative here going to the negative here. Now this same thing, I add another potential difference. My negative goes here, my positive goes here. I connect this leg straight, come and add it to this one. What kind of a bias is this?
Negative.
No, we don't have something like a negative.
Hey, reverse
Reverse,
bias. Sorry,
reverse.
reverse
Perfect.
bias.
Reverse bias. So it means I have my positive connected to the N and I have my negative here. It goes to the P here. Is that okay? So this is my reverse bias. So the junction here is going to be reversed. Is that okay? And the junction here, now we have two junctions, so and the junction is going to be forward bias. Let's think about it in that perspective. Is that okay? Please, any question up to this point? We are building a point.
Sir, please, can you throw a little bit light on it, please?
On which part, I beg?
So that when you continue, I'll not be confused. From what
So tell
I'm
me which
seeing there,
part
is
of
that
your
the left side of the NPN junction, the left side of the NPN junction is negative bias, and then the right side is positive bias. Am I
no.
correct?
Don't say negative and positive. We have a forward and half a reverse.
No, sorry, it's forward bias. It's the first one is reverse bias, and the right side is forward bias.
Sir,
Is that
follow-up question.
what is happening there?
That is not what we just said. We are saying that the first one here,
Okay, you can continue.
The first one here is a forward bias. The second one here is a reverse bias. Is that okay? And this one is a forward bias because our negative here is connected to the N type. So it repulses it to this end. Is that okay? And here, our positive here goes straight away. Our positive here goes straight away to the P type. Is that okay? Making this one a forward bias. When you go to another chamber here, come to another chamber here, the positive here goes to the N and the negative here goes to the P. Is that okay? Making this one a reverse bias.
Say, come again, please. Looking at this one, you said the negative here goes
I hope you
to
can do it.
the N, whilst the positive goes to the destiny. It's connected to the P. That makes it a forward. But looking at the other one, the negative is connected to the P, whilst the positive is connected to the N. That makes it a reverse bias.
When we are talking about forward bias, we are talking about a configuration like this. Is that okay? Where a P is connected, a P here is connected to the positive.
Please go and
Negative
comment
here is connected to the N. Is that okay? Now let's go to this one. You see, the negative is connected to the N. The positive here follows this line to the P.
Listen, why are you looking at somebody's button? Shay.
Hey, please, this thing is on. Oh, no.
Please mute your microphone.
Making this particular cycle, making it a forward bias. Because when you look at this, it's two different circuits we've kind of fused together. Is that okay? And we want to look at it in two different perspectives. And we are saying that the first one here is going to be a forward bias, and the second one here is going to be a reverse bias. Is that okay? Because the N here is connected to the negative, and the P here is connected to the positive. Likewise, here, our negative here is connected to the P. The positive here is connected to the N, making this particular junction a reverse bias. Am I making sense? Yes, sir.
So the principle behind this forward and the reverse bias is that whenever a positive is connected to, let's say, P, and a negative is connected to N, that's when we get a forward bias. But whenever there is an interchange, it becomes a reverse, right?
Yes. And
okay.
We all understand this already, right? because that is going to influence the depletion layer, whether it's going to narrow down or it's going to go high. Is that okay?
Okay, so I'm okay now. I don't know about my brothers.
Okay.
Please, you're also okay.
Very good. Then let me go on. So now let's look at this. If we know that this is a forward, this is a reverse. Ideally, if you are talking about forward bias, does it allow current to go through?
Yes, sir.
Yeah, when you are talking about reverse too, what happens?
It doesn't allow current to flow through because the depletion layer will enlarge or it is widen.
That is for the reverse. Perfect. Now let's look at something here. If we understand this, we can easily move on to the next thing. Now, if I have a situation like this, I think I need a space to draw this very well. Hold on, let me see if I can get a space somewhere. Or better still, excuse me. Disregard. Okay, so now I can draw it very big here. Great. I have one here, one junction here, another junction here. And we are saying this one is N. We are saying this one is P. We are saying this one too is N. And now we are saying that this is going to be forward because at the end, we've done a connection here to the negative, and this is our positive. And our positive here goes here. Perfect. So this is a full circuit on its own because this is a negative, this is a positive, and we've connected to it to a diode. Now the next thing that we're going to do is the second one. This is also a negative. You go to here as negative, positive again. So positive and negative. Then we draw this one here, we go this end, then we connect this one to our end. We are saying this is a forward bias and this is a reverse bias because of how we've configured the polarity arrangement with corresponding to the diode. When you look at this type of a semiconductor, this type of a transistor, which region will be this? Let me start from the middle. Which region will be this? We have three regions. Which regions will be at the middle?
The base.
The base, thank you. And which region will start? The emitter will start. Is that okay? And my collector will be the last one. And from the ideology that we brought in, we are saying that for a transistor, the emitter is heavily doped. Is that okay? Very, very doped. And the base is what? Is lightly doped. And the C is very, very lightly doped. Now, if we have some electrons in here, as many as they are, very, very many, is that okay? And we have some positives in here, but they are not many, very few of them because they are lightly doped. Is that okay? So all the electrons here are many to the extent that when a forward bias, of course, reaches all the electrons, we expect them to go to this end, right? Upon reaching this end, they feel, there's this electron hole pairs. They fill the holes. And at the end of the day, because this one is super doped, like heavily doped than what we have here, Do we still have some holes left, or we'll still get some electrons left?
Excess electrons.
Perfect. We will have a lot of these electrons still left. Is that okay? Because we have more electrons from here to here. Apart from even the base being lightly doped, the base is very small. And you can think about it is like the government coming to your community, and the government, as many as the youth there are, the government select elected people to give them money. Is that okay? And that is what our government have been doing recently. For the past 20 years, every government, it comes and they just have a way of channeling the resources. So after that, we still have a lot of people being a standby one way or the other. And here, the electrons is going to fill in the holes. But upon reaching there, the holes are very small. So the pairing that is going to go on is insufficient. We still have a lot of electrons being janked at the base section. Is that okay? Here we have a collector here. But the collector, we have some electrons. But I told you they are lightly doped, so very, very small electrons here. At the end, we have excess electrons here. We have less electrons here. What do you think will happen to the junction here?
So, Rabbi, I think that some of the excess electrons at the middle at P will cross to the collector there.
Okay. Yes. What do you think will happen?
Hello, yes. Yeah, say,
Mm-hmm.
at that junction, because I think there'll be a repulsive force that will widen up a gap or create a gap there.
Okay. Yes. Any other option again? Remember, now we have a lot of these electrons here. And the ratio that we are even talking about is about 90 to 1. 99 is to 1. We have a lot of these electrons being junked here at the base part. We have very few of these electrons here. We want to know what will actually happen to that junction.
Oh, okay. Now, would the source be
Hello.
in section?
Hello, sir.
Okay.
Yes,
Sir,
yes.
my opinion is that even though in this case we are supposed to have a wider depletion zone because of the excess electrons at the P part now where we have excess electron, they can now cross over and move on to the end regions. That's what I think. Because
Perfect.
under
That is
normal
what is going to happen.
circumstances, okay.
That is what is going to happen. And then continue with the normal circumstance, please.
Under normal circumstances, with our normal connection of reverse bias, they are not supposed to be able to move because we will not have excess electrons at the P part. The P will only be filled by holes. But in this case where we have excess electrons, I think the P part is also functioning as a form of N type. That's why we have excess electrons now.
Okay, so let me follow up. Under normal circumstance, anytime there is a bias, we expect a holes and electrons. But this time around, there's no hole here. We are talking about excess electrons and very few of these electrons. And interestingly, the polarity here, the positive, its mentality is going to pull, its mentality is to go and pull the electrons here and attract them. Is that okay? It reaches here, the electrons here, they are not even enough. We have excess of them here. So it goes and pull what we have here rather. Is that okay? And that is what is going to allow the electrons to flow from this end through the base to the collector. And in actual fact, some of them do pass here, but very, very few because of the very small holes we have in there at the base. So we have about 99% of these electrons actually reaching the collector. and very few of them reaching the base. Am I confusing the class?
Please, we can
No,
come.
sir.
So it means we can go on.
So,
Now I did a diagram here. Mhm.
so I want to find out. Okay. So this diagram,
Mhm.
are we maintaining the two sources there, or we are considering only one, the battery?
No,
I just want to be clear.
for a typical transistor, it needs these sources before it will work. You connect
The
only
two,
one, it's going to be only two regions that you want it to work. And that is not
okay.
what we want. Is that okay? So when you look at a typical configuration like this is my emitter, this is my base, this is my collector, and these are my potential difference in
Okay, then why did we bring in the issue of there'll be forward bias and there'll be reverse bias?
schools. And even the yes, there will be a forward bias in here on my network. Hello, can you hear me, Abeg?
Yes, we are listening, sir.
So when it reaches here, the electrons here, the pairs that happens here will not be enough. So most of them will go here, as I explained earlier. But I've made some points here for your reading sake. Is that okay? So when you look at the first one, we are seeing that the majority of the carriers in the N-type material, N-type emitter material are electrons. We understand that. The base emitter junction, this particular junction, so the junction between the base and the emitter, is a forward bias. We've explained that. To these majority carriers, and the electrons crosses the junction and appears at the what? At the base region. That is the first thing that happens to it. Now let's look at something. The base region is very tiny and only lightly doped. Is that okay? And lightly doped. Is that okay? With holes. So some recombination of the holes occur, but many electrons are left in the what? In the base, which I've explained that. And the last thing that we are supposed to happen is the junction that we have there. We especially or intentionally we expect it to be a reverse, but it's not going to be like that. Exactly, it's going to be just a forward thing because of the electrons that we have excess at the base that is going to the emitter. So at the end, large portion of these electrons here just crosses the what? The emitter, base emitter junction to the collector region, creating a what we call the collector current. So from here, everything that is going here, we are saying is a collector what? Current. Any questions so far? There's another build up.
Junior, mama me sure. Mama me sure. Na me kata bi o.
Okay, so in this configuration, it means we have two types of current. We have the collector current, and then is it the base? Is it the base current is small? Okay, yeah, the base current.
What did you say?
Hello.
Yes. Okay, I want you to throw more light on the reverse bias. So what is the battery doing there? When it's a reverse bias, we all know that it means at what point will this transistor not function?
At what point will
because you said earlier on that before the transistor can work, the two sources must be there at all costs, right?
Yes. So if one is not there, maybe it will not function. Because at the end of the day, we need this one to actually pull everything that we have from here. Sorry, at the base to this end. Is that okay? So if one source is not there, it's not possible that it will work. And this is with the condition of the doping effect. Is that okay? We doping one section more, we doping one section less, we doping one very, very less. Is that okay? Now, let's go on to something here. Now, we understand the electrons movement in that configuration. Now, let's talk about something. Ideally, for N, Pn, we expect this one to be a forward, as we said earlier. We expect this one to be a reverse, as we said earlier. But because of the doping effect, that is why electrons tend to cross through all these ones. Is that okay? Now let's look at something here. If we have a junction like this, for a forward bias, we all know that it allows current to go through easily, right? We all know that. Very good. And there's a very low resistance or less resistance in there. Unlike the reverse bias, that one, it accumulates some voltage. So it reaches its breakdown. And there's a very high resistance in there. Is that okay? So inside this junction, we can have a resistor to represent them. We can have resistor A and we can have resistor B. Is that okay? And now let's look at something. We expect that for the resistor B, that is the second resistor, should have more high resistance in there, and the resistor A should have a very low resistance in there. Is that okay? And if that is the case, we can actually have something we call the power gain. Is that okay? Please excuse me. Let me do this.
Hello, colleague. Hello, colleague. Hello, please. Is our organic chemistry lecture coming on as scheduled, or it's been postponed or rescheduled? If it's coming on as scheduled, then I think that at 11 we have to alert a wrap so that we prepare for the organic chemistry. So if Castro, if you are here, can you react to my comment?
We will close at 11 from this. So it's not yet time.
I'm only asking whether it will come on because you see, we started this class very late. That's what I'm asking. I'm sure that if you had not started early by this time, we'll be wrapping up. So maybe we might have to reschedule the continuation of this lecture. That's what I'm asking.
Oh, okay. Is Castro on? Castro? Maybe he's not around.
Castro is off. It's offline.
If the current through
Mark, are you at West School?
Yes. I am where school now.
Yeah, hello.
Is that face to face?
Yes, there is face to face.
Okay, can we continue, please? Okay. Hello, can you hear me? Can we continue?
Yes, sir.
Okay. Great. So the two junctions, I told you we can have some resistance in there. Is that okay? For the first one here, that is acting as a forward bias, and there's a second one here that is acting as a reverse bias. So this is going to be our output. This is going to be our this is going to be our input because it's coming from in here. Is that okay? And this is going to be our output. Now let's look at something here. We want to try and relate our power gain in here. Is that okay? Now what we have to do is, if we have power, we can actually write power and represent it as power and relate its current and resistance as I squared times what? Times R. Is that okay? And we know that the output that we have here, we are talking about the RCB. That is the collector base junction. Is that okay? And the one that we have here as our input here is going to be the base emitter junction. Is that okay? And power gain is always the output over the input if we are relating it in this part. So it means that this is going to be our output, this is going to be our input. Please, do you understand?
Yes, sir.
Yes, please.
Now it means that if we have this, it's still the same current. So we will cancel our I squared, and now we have our RBC over RB. Is that okay? And this is just the power gain. Now we can also look for something we call the current equation in here. Anytime a conventional current is going through a circuit, does it move from the positive to the negative or negative to the positive?
So it's negative to the positive.
Okay. Any different answer?
So I think it's the opposite.
Positive to
It's a positive to negative. Is that okay?
Yes.
Anytime
Yes, sir.
conventional current is moving, it moves from the positive to the negative. And electrons move opposite direction. So if it's moving positive to the negative, electrons move negative to the positive. Is that okay? Anytime it's moving, it moves opposite. Now, you remember that our electrons were moving, if you have something like this, our electrons were moving from the emitter to the collector. We all remember that. If the emitter is going this way, it means our current is going to move opposite. That is why you see this kind of a movement. Is that okay? Now our current now is moving from the collector to the what? To the emitter. And I told you that a lot of electrons are actually being jumped from the emitter to the collector. And a little of them goes to the base. So it's the same way the current is going to behave. A lot of the current is going to move from the collector to the emitter, and a little of them will go to the base. Is that okay? Very, very small of them. Now, if we are considering this, we want to derive an equation for a current. And even from Kirchhoff, you remember Kirchhoff? Kirchhoff gave a rule under current, not the EM field one, under current. You remember what he said?
Yes, sir.
Can you help me with that?
I said that the sum of current entering the junction is equal to the sum of current leaving the junction.
Perfect. Is that okay? And now when you look at what we have here, this is our junction. Our junction is here, and here the emitter, sorry, the base is fusing in from this end, and the collector too is fusing in from this end, and it goes to the emitter. Is that okay? So at the end of the day, it means the emitter that we have here is going to be equals to that of the base and that of the what? And the collector. And that is how we manage to get this formula. Is that okay? As IE equals IB plus IC. Please, do we understand?
Yes, sir.
Now,
Yes,
let's
please.
go. Now, we can also find something called the current gain. I've showed you how we can manage to get the power gain. We can find something like we call the current gain. Is that okay? And for the current gain, we are not going to factor in the emitter here. We are considering only the collector and the base. Is that okay? And of course, because we expect more current to be at the collector than the base, our voltage gain is just very simple. It's just the current of the from the collector to and divided by the current from the what the base. Is that okay? It's just going to give us the current gain. And this is very important because we have to look at something called the leakage current, and this one to influence the leakage current a lot. Is that okay? Now let's look at something here again. Yes, leakage current. I didn't know it's even following up. So the leakage current here is, you see, everything that we were talking about the NPN was it electrons or holes that we were talking about? The holes, which of them were we saying it was moving?
Electrons.
Very good. It's basically electrons movement in the NPN. Is that okay? In as much as we have a hole in between, the electrons dominate this kind of a configuration. Now, if this is happening, the majority carriers in a transistor for NPN is going to be electrons. But interestingly, we have some minority carriers too in there. Is that okay? And here our minority carrier is going to be holes. Is that okay? So there are holes in there. And I told you that even from our previous understanding of this, anytime there's a movement, there are a lot of things that influence the ejection of electrons or say the holes in their movement. And one thing we said can be a source of photons, ejections, can be a form of EM fold, it can be concentration gradient, it can be thermal energy. Is that okay? If there's a thermal generation, yes, Bismarck.
Yes. So if you look at the circuit diagram on the board, like what I was asking, yeah, you could say that the source is only one for the two connections. But we expect conduction should be happening here.
Yeah,
But in
no,
my
this
earlier
one.
question, I said, is it possible for the diode, the transistor to conduct without the second source?
No,
I
it's
think
not
you said
possible.
no. But this one is only one.
This one is just for an explanation of the leakage current, the minority carriers. Is that okay? So when you see a follow-up that we did, you said, you see we've drawn another one to attach. Even if it's one, drawn another one to still attach. So we still need two sources. It depends on the configuration. Is that okay?
Okay, all right.
And with that, say Rabbi, I think also that for the first diagram, you see that it is connected to N, only two. There's no connection to the third one. And second diagram too, the connection is N to N. There's no connection to the P in the middle.
The same can be okay. There's no hot.
There's no third connection to the P in the middle.
The P in the
middle. The second diagram. Yeah.
That should tell you that some of the sources are being taken away. That's why this connection is possible.
So that is why we don't have two sources of power.
And this is talking about charges flow. Yeah, we are using to explain charges flow. It means conducting or.
Yes. So what I'm using this configuration to do is to just explain the leakage current, the minority movement. But on a typical application of a transistor, say to serve as an amplifier, we need two sources for it to work. And I'll show you this in our subsequent slides. Is that okay? It's very typical example. We need two sources for it to work. Unless, of course, we are dealing with something like a common emitter, a common base, that one too I'll show you to you, where one of the regions serves as a common, and the only region that is actually working is only two of them. Is that okay? But for a typical configuration of a transistor, we need two sources separately to be configured and to be merged and connected. Is that okay?
Yeah, there is something you show your previous slide. There's something I want to understand the previous slides. The previous slides.
This one or which one?
No. Please go back. The gain where you had the gain current and something. Okay, another one back, please. Once the yes. This particular one. I saw something here I need some clarity.
Okay.
Yeah. Yes. We said one of the junction has high resistance. What is attributed to that resistance?
Can someone help me here?
Hello, sir. I think I can help. I think that region with high resistance is the region that is supposed to function as it is supposed to have a wider depletion zone, or the connection is reverse bias, but the electrons are able to move over because we have excess electrons of them at the P side. That's my opinion. Hello, sir. Is it clear?
So is it clear? Sir Bismarck, where is he?
Yes. So that is the point I am trying to establish earlier on that So the current that is flowing, because of charges flowing from the base to the collector, that's what you are calling the IC. Is that what you are calling the IC?
I see.
Yeah, there's an IC there. I don't know whether some
Is it
previous
here or
some diagram. Now there's a diagram they show an IC.
don't complicate what we do here
Okay.
and the other one. Here, what we are explaining is
Yes.
power gain. Is that okay?
Yeah.
And we are just relating the resistance that we have at each junction.
Mm-hmm.
And we have two junctions in the transistor. We have a junction that comprises of the base and the emitter. We have another junction that comprises
There's
of
another circuit there, then. That maybe another slice back. Then I'll show you something there. I just need one slice back.
This one.
No, please back. Please go back. Another one. Then maybe go back another slice back. Yes. This particular this diagram.
Mm-hmm.
Yeah. So you could see that. No, not this one. That one is clear. This one is clear. Yes.
Is it this one?
Yeah, this particular one. All right. Fine. So that was the question I was asking. Why those two junctions? I think my other colleague has explained that. That junction is forward bias. Reverse bias. Yet charges are flowing to constitute the IC. So is there any difference between the current that is flowing through the collector and then the magnitude of the current flowing through the base? Can we compare these two currents? Is there any disparity between these two currents?
Yes. When you are comparing, okay, so the current going through the base, ideally we expect it to be very small. Is that okay?
Okay.
Then the current going through to the collector, we expect it to be very, very huge. Because at the end of the day, what we have in here, or the PD that we have in here, is not sufficient to pull everything that we have in here to the base part. So when you look at even the diagram that we have here, the arrow is showing a very huge current that is going on to the collector. And I mentioned it that we have about 99% of the electrons that we have here goes to the collector, and only about 1% goes to this end. Is that okay? So it doesn't mean the two of them are not functioning.
Okay, so this is because we established that the other junction is of high resistance. Why do we have huge current flowing through it?
Okay, I think we are complicating these things. What we are talking about here is electrons that we have a lot in there. Ideally, as I explained earlier, ideally, we expect this one to be a forward bias. We expect this one to be a reverse bias. Ideally. But as I explained earlier, every transistor has the emitter very, very good. That is at the emitter. We have less doping at the base, another less doping at the collector. That will influence this transition easily. So here, instead of the reverse bias, we still have some electrons go through because of the doping issue. And I came back to the slide and I said that ideally, the two of us should know that if we have a PN, we have a N here, we have a P here, we have an N here, we expect this one to be a forward bias. Ideally, supposing we don't have any more doped electrons or something in here, this is supposed to be a forward bias. This is supposed to be a reverse bias. And it's through this one that we are establishing the subsequent slides. Is that okay? So this one, I'm done explaining this one. With the doping and the electrons that we have plenty and the movement, we are moving on to another thing, establishing something we call the power gain and the current gain.
Okay.
Is that
okay? I'm also thinking that because of high dope nature of these materials, charges flow can be haphazard. So maybe the configuration is trying to establish that for the second source, we are blocking one of the junctions to allow the charges or the current to flow in one direction. So I just want to know the importance of the other source over there in the circuit. What it's trying to do.
Which junction are you blocking to influence something?
Yeah, so the second electrical source, the second source over there, maybe theoretically, what is it doing there? And it's
No, Service Mark, I don't think we are understanding this thing. So we are still complicating things. We have two
why is
things
that
here.
it will not conduct?
We have two circuits, one circuit here, another
Mm.
circuit. Is that okay?
Yes.
This
Yes.
circuit here, influence is by this junction. That is what is working on, period. This one is also working on this junction. That is what is working on, period. Is that okay? Without one, you don't have a transistor function as a general transistor.
Okay.
So it's not about whether we have one, there should be no one, and there should be only one or two. Is that okay? And I explained this one previously that if we have, oh, where is the thing? If we have a
All right. So what happens if you remove the reverse bias, you remove it? What will happen to the circuit?
nothing will happen. It will not function as a transistor. Huh? Hello.
Hello, sir. I'm listening.
That is what I'm saying. It will not function as a transistor. Now, supposing we clear
Okay. Then sir, why will it not function?
Supposing we clear this one as a transistor, you are complicating things too much. Can someone help me here?
Sir, I think that if without the sandwich of the P, NPN, and PNP junction, then we are talking of ordinary diode, boss. So that will be a diode. It is not a transistor. So we are applying the two so that the two now function as a transistor. And now, if you want to ask the function of a transistor or the reason why you are using a transistor, then be clear. Be clear that what is the essence of a transistor so that you be given. Because I think we have not landed. It's a question I want to ask as a follow-up when says if we are able to establish why we have the collector, why we have the base, why we have the emitter. That's what I want to follow on. But I think that we've not gotten there yet. So if you
Now
can
the
wait,
point
but
if
without,
you listen,
but
hello,
boss,
hello,
let me
a
finish.
wire.
But let me finish. But without the two of them, without the three, it is a diode ordinary diode we are talking of. That is what I want to say.
Okay,
Hello.
so
Hello.
the point I'm making is that yes, and as what we are saying, even if it is one source, you can extend the wire and then you can connect all the bases. That's the point I'm making. So it's not about whether it is one
Yes.
source, there is a diode.
Hello.
Yes.
Yes. Like you said, a transistor is a three-terminal semiconductor device. So, like you're saying, if you connect only two sides, like my brother just said, it's like you are making it work like a diode, but not as a transistor. So for it to work as a transistor, all the three terminals has to be connected, and that's why Sir was trying to explain. Do you get it?
But without even the battery, you can extend the wire to connect the three terminal. It is possible.
Yeah, but you see, the explanation he's trying to give, he was trying to explain not the function of the transistor alone, but was trying to explain what happened at the junctions. Do you get it? He's trying to
Yes.
explain what happens at the junctions, but not the function of the transistor.
But you see, he used okay, all right. In this case, we also want to, because that was a general explanation that he was giving of what was happening inside the transistor. But we didn't talk much about the issue of the voltages applied, which was very clear. With the explanation of what was going, but the voltage applied. That is why. So if you could see that, if you look at the
No, you see, he was
Yes.
talking about a specific thing that happens or a specific action that occurs within the transistor, but it was not generally talking about what the transistor does. Are you getting it? So that's why he was telling you that your question was trying to be a little bit confusing, but he was speaking about a specific thing that happens in the transistor and was trying to explain that when you connect two, let me say, two sources to the transistor at different junctions, this is what happens. That's all. So you just take it from that line.
So always we connect two sources to the base all the time when you are dealing with transistors. Is that the case?
No, not is not always, but he is trying to explain. Let me say an event, or let me a phenomenon that occurs when two sources are connected at the same time to a transistor, but at different junctions. You
My
see,
simple
so
question is why must one region or one side of transistor be reverse bias at all costs, and why the other one forward bias? I think that's the
no,
fundamental of
it
my
depends on
question.
what they want the transistor to perform, the function they want the transistor to, like, is it rectification, is it amplification, is it as a switch? So there are reasons, the reason is based on the function you want the transistor to perform. That's
And
all.
I also added, will it work in the absence of one source or not? And he said no.
Service mark.
Yes, sir.
Hold on. I beg.
Yeah.
We are complicating things. Let me finish with the slides. And
Okay.
if your understanding is still not clear, then
Yeah.
we come back. Other than
All
that,
right.
we will just. Is that
That's okay. No, that's okay.
So yes, so here I was explaining the fact that we have something called the leakage current, and the leakage current is, if you remember, we explained something or we learned something where a minority carrier can even move, in terms of some other influences, like any source of energy that it gets apart from the EM4. Is that okay? And that is what happens here. So a typical example as what we have in here, if we have a transistor here, our NPN here, and we connect, of course, our potential difference to it. Of course, we're expecting an electron to move here. But generally, we have some minority carriers that may move at its inverse direction. And here is going to be our holes. Is that okay? And this can actually influence. Yes, George.
Sir, please, when you were out, I was asking my colleague that would the organic chemistry come on as planned? If yes, then I think this is the time we have to break and then organize ourselves for the next class. So if we can wrap up,
And the
please.
next class is what time?
I think it starts at 11:30 to 4:30 or so.
It's eleven
I'll,
fifty.
It's
It starts
11:50.
11:50.
11:50.
Okay.
so
But even if it's 11:50, we still have to wrap up
yeah.
because we started earlier. So I was wondering if we can reschedule the continuation of these lectures. Other than
Oh
that,
no, I'll finish right
even
now.
until
Don't
we
worry.
end this, we have to start the organic chemistry.
George,
Thank
don't
you,
worry.
sir.
I'll finish right now. Yes, I'll finish very soon. So apart from today, I don't want to do a class again. I'm very, very tight. Is that okay? Next week, I heard you have to come to do practicals. And this week is very busy. So let me try and finish it, Albert. Now, the leakage that we are talking about here is very important because at the end of the day, if the leakage actually increases, it will affect the efficiency of the transistor. Is that okay? So now we have a formula where we can actually relate the leakage that is going, we can relate the current gain, and we can even relate the leakage that it gets to the what? To the end part. Is that okay? And I don't know, maybe one way or the other. It's not very important in this slide, but I just added it up. Selma, please mute yourself. So we can have a formula like this where we can talk about the current that is going from the base to the emitter, sorry, the base to the collector, that's the collector base junction, and we can have a formula relating it to the current and the emitter. Is that okay? And we can, of course, bring in, the beta. The beta is the current gain. So if we have this formula, we can actually calculate the leakage that is being influenced by this particular minority carriers. Is that okay? I brought a question here for you to go through. We didn't go through the the PNP. What we did was the NPN, but it's the same. As we explained for that of the electrons, where we have some electrons moving, we have some holes here, and we have some minority of these electrons here. The holes is just the inverse. Yes, Sir George.
Okay, sir. So in which of the case is it now functioning as an amplifier, or that's the part I wanted? Because if we should leave that small portion, maybe the explanation wouldn't be clear. So from what we have
I,
done so far, in which
I have it.
state can you say that when this thing happens, then the transistor is functioning as a amplifier
Hold on, you will
or
see
the
it.
other
I'm not
function?
done with the
Please,
I'm
thank you.
not done with it. Yes, I'm not done with the class. Hold on. We still have a lot to do. So just hold on. You reach there. Is that okay? Are you okay,
Okay,
Sir
okay,
George?
sir.
Your hand is
Okay,
still up.
okay.
Yeah. Uh-huh. So now we have I have some questions here for you to try it out. And this question is very important because I think the A and B you can easily do it, but try and go through the last one very well. And the last one is telling us that if you have a PNP, what will happen to the holes and the electrons, and what will be the behavior of the emitter, what will be the behavior of the collector, what will be the behavior of the base. Is that okay? And here is the same ideology as I use the electrons to explain, where we have some electrons as XX at the emitter, moving on to the base, and finally to the collector, where we call it the collector current. Is that okay? Now, if we have the holes, it's still going to be the same. So we have some excess holes. It goes into the base. There's going to be a less electrons hole pair there. The rest left there is still holes. Most of them goes to the P part. Is that okay? So it's still going to be the same. But the only thing that is going to change here is the power supply configuration. Is that okay? Now, at the end, we expect that P should be connected to N here. We expect that the N here that we have here should be connected to the positive here. The same way, we expect that the P here should be connected to the positive here. We expect that the N that we have here should be connected to the what? To the negative here. Is that okay? To the configuration change as compared to the NPN that we did. That one, we're having a polarity of, say, the positive coming here and the negative, and another positive and a negative was here. And we're having only a positive and a negative. So if you are asked to draw, know how the configuration actually works here. Is that okay? Can I go on? So this is a trial work for you to try for me, I beg. Please, can I go on?
So, Doc, so this
Yes,
circuit,
you
the
can.
circuit,
You
yeah,
can.
okay, that's okay, yeah. So again, it has made one side reverse bias if you go by the connection.
Very good. One side
Mm.
forward and one side reversed. Should I go on? Now, the question that you asked, Sir George asked, how do we get a transistor as an amplifier? And this is how it comes in. When it comes to transistor operation, its physical life operation, we have to get one part of the sections of the transistor to be a common. Is that okay? So we can have an emitter as a common, we can have a collector as a common, we can have a base as a common. Is that okay? And depending on how you want the transistor to behave, it will depend on how you choose any of these ones. Is that okay? So if you take something like a common emitter is typically used as an amplifier. When you have a common collector, it has its own application. When you have a common base, it has its own amplification. Is that okay? And anytime you have a common emitter, we know that the emitter section here is connected as a common. When you say common, connected to, say, the neutral or say the earth or anything. Is that okay? And we expect that the base is supposed to be the input, and the output, we should take it from the collector. Is that okay? The same way, if we have the collector as a common, we expect the base to be the input, we expect the output to be the what? The emitter. Likewise, if we have the common as the base, we expect the input to be, what will be the input here?
The emitter.
No, look at this one very well. It's going to be the collector. And where we have the direction, that is where the region emitter is. Do you remember? Where we have this arrow, that is where the emitter is. Or you
And I said the
forgotten?
emitter. Yeah.
Ah, you said the emitter. Ah, sorry. So that is the emitter. So, and the output is going to be the collector. Is that okay?
So, sorry.
Mm-hmm.
I see the network was worrying me. So if you can throw more light on the common, why do we call the common bill common emitter? What does it imply? What does it basically mean?
Okay. So you
Hmm.
see, any power source that we connect, we have a neutral to it. You understand that? It's like even your house, the AC that you have a live and neutral. A DC to have a positive and a neutral. Is that
Okay.
okay? The neutral is a little bit as the earth of it. Is that okay? So we have three
Okay.
terminals. Whatever being the case, if you want to apply
Mhm.
them, one section has to be the neutral. One
Okay.
section is supposed to be the input. One section is supposed to be the output before the configuration works. Is that okay? And depending on how this configuration works, that is what is going to help us influence or know the application of it. So if you're using as a rectifier, we have one particular one that you have to use. If you have to use it as an amplifier, we have one that you have to use. If you have to use it as a switch, we have the one that you have to use. Is that okay? So the configuration actually influences it a lot. Yes, please, Sir George, come on.
Okay, sir. I was thinking that, for instance, if you want it to function as an amplifier, then maybe the emitter, everything will be pointed to the emitter, so that what will go out, the current out will be higher. I think I was wondering if there's a specific arrangement for the various components, for depending on how you want it to function. I
Sir
don't know if
George,
you
I'm
get
not.
my question.
No,
I
no,
don't know if you
please
get.
come on.
I'm saying that I was thinking that if you want it to have to function as an ammeter, then maybe it must be PNP. If you want it to function as a collector, it must be NP. And that is what I was wondering.
No, no, no,
Or
no.
there's
So
nothing of that sort.
if you want to, the emitter and the collector thing is just the excess of the holes and the electrons in there, and that one was just an explanation of how we get current to or electrons to pass through the transistor. The application depends on the configuration of it. Is that okay? You can someone right now, the two of us can go to market, go and buy a transistor. You may use the transistor as an amplifier. I may use it as a switch, depending on the transistor we went to buy. It could be that the transistor they are all PNP or NPN. Is that okay? But maybe you go and buy a transistor that is a common emitter. I'll go and buy a transistor that's a common collector, and that will influence how I want to use it. Am I confused?
Meaning
Or
that,
we are...
so meaning that the arrangement of the respective semiconductors has nothing to do with how it will function. It will depend on how you will connect it.
Not how you connect it, how it is. Hold on. I'm saying that the transistor's configuration is in three. It's something that the manufacturer has done already. Is that okay? How you connect it, yes, it also matters. But the manufacturing company, you see, when you buy a transistor, we have a code that we use to buy a transistor. You send that code and go and get it. When you buy a transistor, it's not every transistor that is used as a switch, as an amplifier or something. So if I want to use it as a switch, we have a particular code to buy it. And when I'm going to use the code to buy it, the manufacturer knows that because that code, you want to use it as a switch, you need this kind of a transistor before it will work. If I want to use it as an amplifier, we have a code to go and buy it. It knows that we need a common as an emitter before it will work. Sir George.
Okay, I'm okay. I'm okay. Thank you.
Now, you are very familiar about this when we are talking about voltage or current voltage characteristics curve. We did that during the forward and the reverse bias. Please, do we remember? Do you remember anything like that? Sergio, do you remember something like that? Hello, am I online?
Yes, Rob, you're online.
Do you remember we did something like a curve characteristics where we have something like a forward bias, something like this, and we have a reverse bias, something like
Yes,
this, where we have a breakdown around this end, and we
yes,
have
yes,
a place like this as our new voltage. Remember all
yes,
these things, right?
yes, sir.
Very good.
Yes.
We are going to go through this thing very briefly. And we said that, if you remember, that for the forward bias, if we have something like this, because our current was here and our voltage was here. Is that okay? Now, if we are going this path, it means we are increasing voltage. And if we are going this path, it means we are increasing current. Is that okay? For a normal ohmic material, it will behave something like this. Go straight. It means current is increasing with
Okay,
respect to
please.
voltage. Yes, Eric, you said what?
The screen.
You are not seeing.
Yes, please.
Is it only you? Please, or everyone?
So it's showing. The screen is
It's
showing.
showing. Please check your network, I beg. Is that okay? So the ohmic material is behaving like this. It means current increase with respect to voltage. When it comes to a semiconductor, it's not an ohmic material. And we said that how the current moves influences how the of course how the voltage is going to move. So here, something like this, it means anytime we increase voltage, current, there's no current going through. You increase, there's no current going through. Unless it reaches a point where we will get some current go through it. Is that okay? And that point that we said, you let the current go through is what we're calling the new voltage for the forward bias. Is that okay? And we said that even for silicon and germanium, it has different voltage points that it will allow current to go through. Do you remember something like that?
Yes, sir.
Yes,
Okay,
sir.
very good. And again, we even said for the reverse too, if voltage is going through, current will not. But the time will come, the barrier will break and all currents will go through. And that is what we call the breakdown. The same way we have in these common regions, common emitter, common collector, common base. We have the same phenomena going on there because at the end of the day, it's still another PN junction that is going on there. Is that okay? So we will just go through briefly the common emitter. Is that okay? For the collector, we may not do it. For the base, we may not do it. Is that okay? So we just go through this one and we will look at it in with respect to the forward, we will look at it with respect to the reverse, and we will look at it with respect to both the input and the output. Is that okay? So this is for so this is how a typical configuration looks like for a common emitter. And here, a typical one, we expect the emitter to be the common. When I say common, connected to the neutral. Is that okay? Or the ground or the earth. And when you look at this, we have our current. This is the first configuration. We have the input signal going in this way, and we have a power source connected to it. Is that okay? And we have another second configuration, and we have another power source connected to it. And we have our output here. You told me that the conventional current moved from positive to negative. So here the conventional current is moving this way. The second one, the conventional current is from positive to negative, so the conventional current will be going this way. So this time around, what we expect the current to do, the input signal to go in from here because it's going to the base and it will exit at the what? At the emitter part. Is that okay? Then we get our output here. And here, the most important thing, the common is the emitter. Is that okay? So we call it common emitter. This is the mode of it. Should I go on? Do we have a question here? Yes, Sir George.
Sir, please, I don't mean to dictate to you, but the time left, and then maybe I have to charge my phone some more for the other lecture. I beg. If even 10 minutes, we can reschedule the 10 minutes some other time, I think, so that you not rush a little bit. Some of us, we have had problem with this thing since we started the course. So I think this is the opportunity for me to understand it. So if we rush it a little bit, I think it will be a problem. If it
That,
will not
that
be a much of a bother, I beg if we can
that is
reschedule them
fine.
maybe 10
Yeah.
minutes so that you not
What
rush
is
it.
left? Actually, no. What is left is actually self-explanatory. I've done a little writings around it. Is that okay? So you can go through yourself
I don't
if you have.
understand the last one cry that you are doing, but I think we are
Yeah.
rushing a little bit.
No. Hold on. What we have here is a little bit self-explanatory. Is that okay? So let's go through it ourselves. If we are done, then we don't understand, we can just put it on the platform and schedule a day. Is that okay? But at least let it be today. Tomorrow
Okay,
going
okay.
will be a little tight for me if there's an issue with it. So here it's left with about only 3 slides. I think 1, 2, 3, and this one, and that is all. Then a question for the class, and that is all. Is that okay? So just go through the slides. It's very self-explanatory when you read. Is that okay? Okay. So I'll see you on the platform if there's a need.
Hello, Sir
So,
Ravi.
so Sir Rabbi,
Yeah.
we don't have
Okay.
So please
the
send the slide
slideshow
for us.
Yeah, I'll
right
send it
now.
right up. Yeah, I'll
Yes.
send it.
Sir
Any
Ravi.
question? Yes, sir. Please, I'm here, Eric.
I learned at the onset of these lectures, you said that it's left with some topics that we didn't treat. You asked us to read
Yeah.
about.
Yes. So, do we have the book, the electronics book
Yes, please.
for the code one? Yes. So, any topic that we think we didn't cover up, maybe you can just go through yourself. Is that okay? And of course, if you have a question, you can reach out and we discuss. Is that okay?
Mr. Ravi,
Yes, sir. Ibrahim.
please, could you please plead on our behalf? I'm talking about the coordinator. If there will be some tutorial question for us.
No tutorial questions. This slides, everything is tutorials. We do small, we solve questions, we do small. I have been doing that for a very long time. So that we don't plan another time for questions and answers. Is that okay? No. So go through the slides and everything that is in there. The questions in there. If you're able to go through and you understand them, I think yes, service back.
Yes. Like our
Yeah,
colleagues
Oh
were
God.
saying, some tutorials will be okay. If you look at our
come again.
You wanted to say
from me.
that our colleagues from other courses,
Yes.
for them,
Yes.
sometimes they get tutorial from their course coordinators, and
Yes.
it is really helping. This
Yes.
course
Helping
is,
them.
is,
You
is
see,
very cumbersome,
unlike
and
physics,
you
and we
must
are
be frank with
physics in
us
five, we can
for
do
sure.
something.
And so you sometimes if there is a way out, you have to. We are not saying that you should give us the questions, but some tutorial at least you solve, then you go 1, 2 drop, then you become happy. We are
Okay.
pleading. We are pleading.
Oh,
Sarabi, we are people. Even the physics, people are not interested because of the perception of how it is. And it's not easy at all. So if you can get
so
this an organized
let's
tutorial.
channel that communication through. Sincerely, the course is not me who is taking. I'm just helping teacher Peter teach. So let's get through the course of Kelvin. Sir Kelvin
Okay.
can help us. Then Sir Kelvin has Dr. Peter's number. You should reach out to him, then discuss it with him. If there's a need, then I'll come in. But as I said earlier, sincerely, I have to finish school, so I'm super busy. I have not been sleeping of late. So you
Okay.
talk to him, then if there's a need, then I'll come. Is that okay?
Okay.
So I'll see you if there's a need. Okay. Have a nice day.
Simple new. Say Mark. Say Mark
Yeah,
Bota.
that.
Say Mark Kumasi. Are you at rescue?
Yeah, I'm at Wesco.
So you are waiting for our course tutor.
Yes. I'm waiting for him. He's not in yet, but I'm waiting.
If I knew you would come there, I would have also joined. But just when we were having the online discussion, I got to find out that you are there.
So I'm waiting. I've
Ah,
seen
well,
Frimpong and other guys around.
okay. We also we check to see if the online this thing will be coming on. I'm talking about the course coordinator.
So the what is the name? The practical session to there is online session for some other centers.
But this week is not practical.
Hello.
Next week is practical.
Okay.
This week is not practical.
Oh, okay.
Next week is
The
practical.
practical is next week.
So
Yes.
this week is only face to face, right?
Yeah, but some centers will be having online. Just like when we came the
Okay.
other time, then they were having the online. I'm talking about the
I
UCC
understand.
center and other.
I understand.
Say, Mark Voter.
Yes, sir. Yes, sir. So,
Fache
the
me,
Calvin
Fache
that said,
Zach, Fache Zach,
yeah,
Zach
no,
that you are
that's like,
speaking.
okay,
Yeah,
vote a bit, yeah, Mark.
yeah. I
So,
hope you know the one.
yes, I know.
Fache me,
My
why?
good friend, my good
Sometimes
friend,
you call, I'm busy. Sorry.
yes, yeah, that's okay, that's okay. So, the Calvin that you talk about, is it our course rep?
Yes, he's our
Oh,
course rep.
okay, our course rep. Okay, all right.
I will speak to him if
Yes,
if
you have to,
we see something positive out of it,
and
because
exactly
our
because
course is something
yes,
else, and
yeah, it's something
more to the
else.
point, you are doing
Yes,
the same BEd course with some people, and some their tutors will get them something to read, and it will
yes.
come. And our case
Actually,
is different.
it's not the best. It's not the best.
It's something
So,
else.
it's not the best. It's not the best. So let Calvin talk to the coordinator about this thing. It's very important.
Okay.
Yeah. All right. We'll
All
link
right,
up.
man. Okay,
Yeah.
inshallah.
Bye.